I think both combined will be far better, sir.
Yeah, it's okay. It's good.
We will switch off our videos, sir. We'll all switch off our videos.
Yeah, it's fine. Yeah. Can you see my screen now?
Yes, sir. Yes,
That's
sir.
it, sir.
My PPT.
Yes, sir. PPT. I can see it, sir.
I'm not seeing here. Okay.
Sir, can you please make it as full screen? Then I think you can see that.
In full screen only.
Full screen slide.
Yeah. I'm not seeing my screen. Well, I'll just log. Hello?
Sir.
Here it's telling this will, okay, host will, okay, yes.
Yes, yes, sir.
And because somebody disabled the screen sharing.
Now it can be, sir. Yes, sir. Now it is, yes, sir.
Yeah.
It is coming on the screen, sir.
Yeah, now it's fine, right? Yeah.
Yes, sir. Yes.
Now, my audio is here.
Now it's okay, sir.
Yeah. Yeah, now it's fine. Yeah, so today my work has given to me is basically mechanical properties. So basically, I am mostly touching the basic characterization techniques. This I want to acknowledge one of my collaborators, Professor Ishwar Prasad, and some of the work presenting here is basically contributed by them also. And from IIT Indore, and Professor Angus Wilkinson from Oxford University, and Jay Gong from Oxford University, and Professor Ramurthy from National University of Technical University, Singapore, and Professor Atul Chokshi, IISc Bangalore. So this is my outline, and also I want to acknowledge my students.
Excuse me, sir.
Hello?
Sir, your PPT is not visible, sir.
Is it?
Yes, sir.
You sure? Can you hear me, see me now?
Yes, sir. I can see, sir, but it is not in full slide, sir. Full screen.
Oh, okay. Fine. Now it's fine?
Yes, sir.
Yeah. So I also want to acknowledge my students, Asam Falguna and Sairam Gaud and Mr. Srinivas Dudila for their work, which I am presenting here actually. Actually, I planned my talk in this 1.5 hour presentation. So I planned my talk in, first I will introduce what is the importance of the mechanical testing, and then I'll talk about the different classifications, like how the mechanical testing and the different length scales people do, and what is that, how to characterize depending on what condition, what kind of technique they use, and all those things I'm going to talk about it. And then finally, I'll introduce the conventional uniaxial mechanical testing, which is UTM, and then talk about the what is mission compliance and how to correct the mission compliance, and what kind of experimental techniques are there to minimize the mission compliance and all those things. And then I will talk about the instrumented hardness. It's also called nano hardness, or basically depth sensing hardness. And then finally, I will close my talk with some case studies in micromechanical testing, which I've done in Oxford University. So basically, the importance why we have to do mechanical testing is because we are so many structures which require a significant amount of load bearing capacity, and this is one of the examples, Golden Gate Bridge in San Francisco, which is a total span between the two. Can you see my pointer? Hello? Can anyone see my pointer here?
Yes, sir. We can see your pointer, sir.
Yeah.
Sir,
So
could you
this,
enlarge your screen, sir? I mean, we are able to see the next
slide
layer also.
It will be there in display settings, sir.
screen. Hide previous present review.
Yes, sir.
Now it's not increasing. Now you can see.
We can
Full
see
screen?
all the
No.
slides, sir. Actually,
Now full screen is not there.
not there, sir.
I don't know what I did wrong. Okay, then stop share and then I will reshare the thing. Screen share and share now. Wait, it's not enlarging basically.
Yeah, sir, go to that full screen mode, sir.
Full screen mode is not happening here.
Sir, F5. Please try F5, sir.
That's what I tried. I'm trying that one.
Okay.
Now it's there, but
Yes,
again.
sir. Now you go to display settings on the top of your screen, sir. Display settings on.
Oh, okay. Here.
Yes, sir.
Okay. Swap present review and slideshow. Duplicate slideshow.
Show the option beside that, sir. Show.
So swap. Now it's fine.
Yes, sir. It's fine now.
So just I'm giving a couple of three to four incidents where the load bearing capacity and also the load state of mechanical stress, everything is different actually, and the type of loading is also different. This is basically the Golden Bridge in San Francisco, where the distance between the two supporting beams are basically 120 meters, 1,280 meters span actually. The whole load of this bridge is actually transferred to these beams through these two ropes basically. So this requires a significant amount of tensile strength in this case. So the material which is having sufficient amount of tensile strength have to be applied in this case. So in this scenario, this is basically a what is called basically this guy is shooting the gun to this one. Basically, this is a bulletproof glass. Here is a bulletproof shield is there. So here the loading rates are extremely high. So the material not only withstand the stress, it also has to experience the very high strain rate. So in this application, the material which is having very good resistance to high strain rate deformation is very important. So, and also here the fracture property is also very important, basically because fracture is happening by branching so many branchings, so that it can absorb all the energy rather than like simply 2-3 surfaces can create, then it can absorb very less energy. So more impact will transfer to the basically the person behind the shield. So here we require very high strain rate. In this scenario, this is basically airframe wing actually. So here it experiences, for example, if you see the load as a function of the time, it experiences very like a irregular cyclic loading. So here the basic property what is very important is fatigue actually. So airframe, the fatigue properties are very important for the materials which are going to apply in the airframe fuselage and the airframe wings and all those things. So here cyclic loading is very important. So if you see here, this is a gas turbine engine. So gas turbine engine, this is basically the which generally uses for these aircrafts. So this is the inlet gas, this is outlet gas outlet. So for every minute, it's going to be like this cold air is going to come with very high pressure, and here it's going to combustion will happens. Here the temperatures reaches up to sometimes 1800, 1900 degrees centigrade, and this is the hot combustion zone. Here the blades experience around 1400 degrees centigrade actually, but the actual blades can experience only 1100 degrees centigrade, which is super light. So on the top, there will be thermal barrier coatings and bond coat and thermal barrier coatings, and then also cooling to the blades and all those things will happen. Finally, it can withstand 1400 degrees centigrade. But the point is here, the temperatures are extremely high. At the same time, it has to withstand the combustion, corrosive environment of the combustion gases also. So here, the high temperature strength is important, creep is important, along with the good resistance to oxidation and other things. So here, that what it finally I want to bring it to the notice that depending the application, the priority, the kind of property that is required for a material changes from uniaxial to very high strain rate, high temperature resistance, high temperature deformation to the resistance to cyclic fatigue loading. So here another thing I want to mention here actually, which is basically a simple Carnot cycle. So this Carnot cycle, basically the efficiency of the Carnot cycle gives the T1 minus T2 by T1. T1 is the inlet temperature, T2 is the outlet temperature, by T1 is the inlet temperature. This basically the, for example, if you take any thermal power plant or any other, any heat engines. So basically the inlet outlet temperature, we don't have much control. The inlet temperature we have control. For example, in thermal power plants, so basically the inlet steam temperature, which is basically passes through the once steam get generated, it will go through the superheaters and reheaters to increase the temperature of the steam. So that is the basically T1. Basically any thermal power plant, the operation temperature is basically the temperature of the inlet steam before going entering into the turbine. So the difference between these two is basically dictates what is the efficiency of the turbine. Okay. So in general, the efficiency of the normal conventional Indian-based steel plants is around 35%, 32% like that, which are ultra supercritical or supercritical thermal power plants. But if you increase the further efficiency, you have to increase the inlet temperature. If you take a heat engine thermal power plant scenario, so by increasing the operating temperature of the thermal power plant, we can increase the efficiency of the thermal power plant so that we can decrease the carbon footprint and other whatnot. So this increasing the not only here the gas engines in thermal power plants, if you consider it in the gas turbine engines, which is in the aircraft engines, there also they has to increase the temperature of the heating inlet temperature. So what finally boiling down is basically to increase the efficiency, which is the hour of the need. We have to push the operating temperatures every sector, every sector. Even in thermal power plants, which is around 600, 700 degrees centigrade, they want to go to above 700 degrees centigrade in advanced supercritical power plants. And in gas turbine engines, they want to push to one more 100, like 1200, 1300, 1400 degrees centigrade. So for that, we need to develop a materials which can withstand such high temperatures. At the same time, people are also looking for very high strain rate engines, high strain rate resistance, very high strain rate deformation. So today's scenario is that people are looking for the materials which can apply very extreme conditions, like very high strain rate or very low temperature, like cryogenic temperature, or very high temperature, such like that. So that's why the characterizing techniques also, to understand those behaviors, we have to continuously have to modify. That's just I want to point out here. So now, if you see the now I want to classify the mechanical testing based on the strain rate and loading rate. For example, if you see the bar graph here, this is basically the increasing the strain rate. So depending on the what strain rate or load rating we operating, we have to use a different particular characterization technique. For example, if you're talking about 10 to the minus 7, which is generally a geological length scales, like deformation between the platelets under the earth crust, these kind of things will happen in the above minus 7, minus 8, minus 10 strains per second. The units of the strain rate is basically 10 to the second inverse. So this is basically geological time scales. Then from there to 10 to the minus 4 is very low strain rate deformations, which can happen at high temperatures generally. For example, blades in the thermal power plants, turbine blades in the thermal power plants, or high temperature applications, where the strain rates are generally 10 to the 7 to 10 to the minus 4, which is basically a creep dominated deformation. So to understand this behavior, we have to do more creep tests rather than a uniaxial compression tensile test, which we're going to discuss in a short while. So from 10 to the minus 4 to 10 to the 0 second per second strain rate, this is called quasi-static strain rate, which is generally the most widely studied area, basically, which is basically studied by screw-driven uniaxial tensile machine. This we're going to see in a short while. So if you increase further 10 to the 0 in the uniaxial screw-driven tensile machines or compression machines, we can't do the very high strain rate because that's driven by the screw-driven machine, basically. So there they modified further by using the servo hydraulic machine to further increase the loading rate or strain rate. This is called hydraulic actuator. This is also comes under quasi-static. So 10 to the 1 to 10 to the 4, which is high strain rate regime, where they use a Split-Hopkins pressure valve. Here the strain rates, basically this study is especially important for the bulletproof jackets and for the materials which are going to use in the airframe fuselage, and those kind of materials has to bear the impact of the particle or any other foreign material is very important, how to resist to those impacts. So to study those kind of things, this Split-Hopkins pressure bar is very important. To further increasing the strain rate to 10 to the 4 to 10 to the 5, which is significantly high, they further modified the Split-Hopkins pressure bar by decreasing the size of the bars, so that we can increase and decrease the noise, and at the same time we can increase the strain rate that we can measure. This is called miniature Split-Hopkins pressure bar. And from 10 to the 5 to 10 to the 7, people uses it's extremely high strain rates. So this is like an explosive, basically, for example, materials that can experience these explosives and all those things will experience this kind of strain rates. So these people uses with a plate impact test, where we can't measure quantitatively the strain rate, but we can measure the qualitatively what is the effect of high strain rates on the deformation behavior and all those things. At the same time, we can further classify this mechanical testing based on the stress state. So, for example, if you're applying a uniaxial tension, that is basically applying the stress along a particular direction, that is called uniaxial tension. If you apply the stress in the opposite direction, that's uniaxial compression, and apply the stress in two directions with the uniform, like with a balanced stress, that is called biaxial tension. And this is basically a pure shear, which is basically this kind of torsion kind of experiments we do to understand this behavior, to get the shear modulus. So on the further, people nowadays using the high pressure torsion, where on the top of the uniaxial tension they do apply the torsion force. This is called high pressure torsion, where you can generate extremely high strains. And and also there are something called 3-point bending and 4-point bending is there. And also here we can much easily can measure the elastic model much more accurately. And also we can calculate the cyclic loading, which is called fatigue, where you apply the load in the cyclic pattern, basically the tension, compression, or tension, or irregular pattern, whatever it may be, because this is the stress axis and this is the temperature axis. So the stress increase and decrease. Basically, this is cyclic loading. Here the stress is going to tension and then going to compression and tension, compression. Here it's a tension cyclic loading. It's irregular cyclic loading pattern. So these all basically to study the fatigue loading. So this is how the mechanical testing based on the stress state. Further, when you're doing mechanical testing, this is very important whether your sample size, because sometimes you have very big volume of the sample, and sometimes the sample constraints are very much, so that we can go very small scale basically. So if you have a significant amount of material is available to make the samples, then you can go to ASTM standard sample. And most of these experiments are ex situ experiments. Basically, these we'll see in the open place, and we measure the strain from the cross-set velocity of the machine. And then sometimes the sample size constraint will be there. Then we can reduce the sample size of the ASTM standard by scaling down to lower sizes, by scaling down all the parameters uniformly to the lower size, so that you can do the tensile testing. This also is mostly in ex situ. Right? Sometimes what happens is samples are in the micron scale, where mostly you put the samples under either optical microscope or SEM or TEM, where people do in situ testing basically. So this is based on what the sample size. And also same time, what kind of material you're testing is also important, while you find out which technique you have to use, which property you have to measure. For example, mostly metals and alloys, these conventional structural materials, we will use normal tensile tests. Tensile test and compression test, mostly they depends on the tensile test, because they have significant amount of ductility. General tensile experiments will do when we want to measure the ductility. But if you want to go to ceramics and glass, the ductilities are so less. So the tensile experiments very difficult to conduct. So people generally go for the compression experiments here. And for example, you go to polymers or soft matter biomaterials and all this kind of materials, where there is a viscoelastic behavior which is not observed in metals and alloys. That means there is a difference between the stress to strain response. There is a phase difference between the stress to strain response. So this is called viscoelastic behavior. This generally people studied the cyclic loading and those kind of things to measure this viscoelastic behavior quantity called loss modulus, and all those things we can measure for this kind of materials. At the same time, people also samples sometimes will be single crystal, and sometimes will be like a bamboo structure, and sometimes can be a near bamboo structure, and sometimes a polycrystalline structure or nanostructure or maybe amorphous structure. For example, consider this is the grain size. So if it's monocrystal, then the anisotropy is very much important, because the elastic modulus, if you measure, or if you measure the strength or ductility, maybe the different from one direction as compared to another direction. So you have to always, you have to report which direction you basically cut the tensile sample, the compression sample, and what is the effect of anisotropy on the mechanical properties. A bamboo structure is also similar to, can be considered as a mono single crystal, where the grain boundaries are run along the cross section. So this is basically typically a bamboo stick. Actually, the structure looks like. Here also the anisotropy is very much important. And also near bamboo structures called volleyball structures, there also the anisotropy is very much important. And how to distinguish between the near bamboo polycrystal or actual polycrystal is that there should be a minimum number of 10 grains across the thickness of the sample can be considered as a polycrystal. Anything less than that can be considered as a near bamboo structure material. So once you go to polymer structure, if it's a randomly textured material, then you don't need to worry that much about the texture properties, like anisotropy properties around different directions. And if you go to nanomaterials, where the grain size goes beyond 8 nanometer, 9 nanometer, 10 nanometer, below that one, the grain boundary volume fraction is much more increases much more rapidly. Go to beyond that for 30 to 40%. So there, the mechanical properties are completely different from the polycrystal materials. So all these things you should keep it in mind while measuring the mechanical properties. So now I'm going to start about the conventional mechanical testing using UTM. Hello?
Yes,
Hello?
sir.
Yeah.
Yes, sir.
Is it okay, right? Everything fine, right?
Everything is okay, sir.
Yeah.
Yes.
Yeah. So basically, I'm just going to show two different, as I mentioned earlier, 10 to the minus 4 to 10 to the 1. You can 10 to the minus 1. You can use screw-driven machine, and beyond that, 10 to the minus 1 to 10 to the 1 at least, you can use the servo hydraulic dynamic loading mechanical testing machine. So I will explain how the mechanical testing frame looks like. This is basically a typical Instron tabletop mechanical testing, which is having 30 kilonewton capacity, but we can have the capacity up to 1,100 Newton, 1 ton capacity machines also available, which to test the concrete structures and so whatnot. So basically, this is how the internal skeleton of a mechanical testing machine looks like. So this is basically 2 lead screws. These lead screws will be driven by the gearbox. This will be connected to the motor here. So this motor operates this gearbox. This will in turn rotate the lead screw. Then this have the 2 components. One is this is called upper crosshead, and this is called lower crosshead. Lower crosshead will be this is called lower crosshead. This is called upper crosshead. So lower crosshead is generally fixed. The upper crosshead is movable. So when this lead screw will rotate, this will move the upper crosshead along this direction, either upward and downward direction, depending on whether you want to apply tensile or compressive stresses. And this is basically what you're seeing here is basically called tensile grips, which is connected to the load cell. This is basically the load cell. So generally, the output of a typical uniaxial tensile machine, either is a servo hydraulic or screw-driven, is basically that load you're experiencing, and also the crosshead displacement. The displacement, how this crosshead is moving, and what is the load we're getting from the load cell. These 2 analog outputs, they do signal processing, and finally get the digital signal from these 2. And these are basically grips, and this is called load train. Okay, so basically at any condition, at any cost, the axis of the load train should be collinear with the axis of the tensile sample or compression sample. That is very much important while performing the tensile experiment. And also, you have to choose a proper suitable grips depending on whether tension, compression, or 3-point bending, whatever you want to do. You have to choose the proper grips to hold the sample. So you can perform the indentation. You can perform the tensile experiments by applying the displacement. Then you record the load basically. Because these tensile experiments, the independent variable will be the displacement, and the dependent variable will be the load, experience load. So always you have to be careful. What is the load cell capacity? Because sometimes the output load may be much higher than your load cell capacity. We'll talk about how load cell actually operates. So then we will get much better idea. But the loads, at any cost, the maximum load that you experience during the whole experiment should never cross the capacity of the load cell. Otherwise, it spoils the load cell basically. permanently. So this is basically how the screw-driven works. For example, if you want to apply a cyclic loading, means the tension and compression, but with a much higher speed. So basically, they has to switch over from the movement of from the top to bottom. They has to switch over the direction of the rotation of the screw, and they have to change the direction of the rotation of the gears. It's all basically mechanically operated, which has some limitation in terms of how speed you can operate. So that's why there is you can't do basically high strain, high fatigue experiments in the screw-driven experiments. Actually, you can do very low cycle fatigue experiments where you can apply the cyclic loading, but in principle, these screw-driven machines are not useful for the fatigue loading. There is a hydraulic machine. Here we are having a actuator is there. This will be connected to a hydraulic pump, power pack. And this is basically the again upper top crosshead is the bottom crosshead. This here we keep the upper crosshead as a constant, stationary, and this bottom crosshead can be activated by the hydraulic pump. So it can basically have this this actuator having some ball will be there, which can have the option of changing the loading pattern from tension to compression, like upward direction to downward direction. This actuator and all those things, which can operate much faster as compared to screwdriver. So here you can in this hydraulic machines are much more robust and also much more expensive, and also you can have the facility to operate standards up to 10⁻⁴, and we can also do fatigue loading in this hydraulic UTM machines basically. So this is how what is the difference between the, I think here the actuator is in the up, not down. So this is stationary, this is mover. This is connected to the power pack in this machine. This is basically jig royal machine. So this is how the distinguish between the screw driven and the hydraulic driven machines. So this is what kind of samples typically they use in the conventional tension machine. This is basically a cylindrical cross-section tension machines, which is and this is basically a rectangular cross-section tensile machine. This also depends on what is your sample material, what condition material is there, and what you want to test of the post-deformed material, what you want to do on the post-deformed sample. For example, your sample is more and more forged kind of material and more thickness material is that people go for cylindrical cross-section sample. Your sample is basically sheet form, and you want to study the microstructure of the deformed material in the gauge portion. Then you better to go to the rectangular cross-section dog bone shaped tensile sample, because you can see the microstructure of the sample after the deformation also. And this sample you have three portions. One is basically the grip portion, and this is called the gauge portion. This is the shoulder, and this is the curvature portion. So the cross section of the gauge portion is intentionally kept it lower as compared to the grip portion, so that the whole deformation will concentrate in the gauge portion. So we put a gauge marks, and that is the basically initial this for example, this is the gauge marks. They put the what is the distance between the gauge marks, that is called the initial gauge length. And after the deformation, you can measure what is the distance between the two gauge marks and measure that's the final length. So the difference between the initial to final by final initial length gives the engineering fracture strength. So basically the whole deformation is only concentrated in the gauge portion. Okay, if it's go to compression experiments are basically cylindrical cross section, or it's a rectangular cross section. So this is have the two basic here in the tensile experiment. The basic property is basically your gauge length and your cross section area. These are the two important parameters. In the compression experiments, the length of the sample and the cross section area of the sample are the two important parameters. So here basically there are two very important factors that need to be considered. Is the basically L by D ratio, that is the length of the compression sample to the diameter of the compression sample. For example, if it is rectangular cross section, then you have to get the area of the rectangular cross section and equivalent to the circular area, and then you have to calculate the D, and that is basically the L by D ratio of the rectangular sample. So the L by D ratio, you can't keep whatever randomly the number, because if L by D ratio is above 2.5, basically, sorry. The L by D, I think there is some mistake. Is there L by D is above 2.5, then the material is going to buckle. Basically, buckling will come. Above 5, the material is going to buckle. So that means the length of the sample is much higher as compared to the thickness or cross section area. So the material is going to buckle the sample. This is not a proper result you're going to get. If the L by D ratio is around 2.5 above, then the material is going to shear. This is how the sample looks like after deformation. This is also not a proper, if the sample after deformation is like that, that means your data is not accurate. There, for example, L by D is about 2 and below 2.5, but there is a friction along these samples, because these compressive samples are between two plate ends. These two platens actually, in between the two platens, this compression sample is going to give. So there is a surface between there is contact surface between the top platen and the top surface of the sample, and the bottom platen and bottom surface of the sample. So that there is a friction among this one, which actually basically restricts the deformation along this direction, and if that and also the plastic flow of the material close to the platens, compression platens. So here you won't see much deformation. Here you won't see much deformation if there is a significant of friction is existing. On the top, if your L/D ratio is above 2.0, then there is going to be barreling like this, like a dumbbell shape you get, and barreling in the upper portion, barreling in the lower portion. There is no deformation along the central portion of the sample. That means it's a non-homogeneous deformation. This is also not a proper way of doing compression experiments. If the L/D is 2.0, still friction is there at the surface, then again basically there is no deformation at the top portion and the bottom portion of the sample. So the most of the deformation concentrated at the center portion of the sample, because the deformation along this zone and the deformation along this zone called dead zones, and you won't see any deformation. The deformation mostly concentrated in the center portion of the your cylindrical sample, and this results in the barreling. This is again a non-homogeneous deformation, and this is also not a proper way of doing experiments. And the way of reducing the friction is by applying some kind of lubricant on the top and bottom surface of the sample before putting into the between the platens. Molybdenum silicide and some grease, this kind of lubricants we keep it, then it can reduce the friction between the platens and the sample surface. So it allows the material to flow and along this direction in the top, close to the top and bottom surface also, which can actually create a uniform deformation. So this is a more accurate way of doing compression experiments. Another, the difference between the tension and compression experiment you have to keep it in mind is that when you compare the data of the tensile data and compressive data and say that there is a difference in the tensile and compressive data, then before making that comment, you have to remember that in the tensile experiments, there is a restriction. For example, hold the sample along here and here. That means the sample is not allowed to flow along this direction. Only the sample is allowed to move along this direction. Whereas in the compression experiments, the sample can flow freely along lateral direction also, and unlike the tensile direction. This can create some kind of difference between the the material properties in the tension compared to the compression. So you have to basically correct the these kind of things and then compare the data between the tensile and compression. Then you can comment there is anisotropy in the tension compression properties, anisotropy in the properties in tension and compression. So another thing is basically that is how the sample looks like, and then how basically the load cell, how it operates. I just want to mention, bring it to your notice, because this is how a typical load cell looks like. This is cylindrical load cell is called standard load cell, which generally you see in the for example, what you fixed here, this is basically the load cell here. Here basically the load cell is there. These are standard load cells, or there is a shaped load cell will be there. So the load cell in the top section, it looks like this, and you cut the surface, it looks like this kind of structure will be there inside the load cell. And the sample, your pull rod or push rod, the sample is going to fix to this portion. There will be grips, and then you fix the sample there. Hello, can everybody hear me? Hello?
Yes, sir.
Yeah, sorry.
Yes,
Because
sir.
I'm speaking, so I'm speaking like I am talking to myself. That's why sometimes.
No, sir, it's audible, sir. Clear, sir.
Thank you. So basically, this is basically if you apply the load along this direction, either uniaxially tension or uniaxial compression, then these arms are there. These are going to deform significantly in the out of the whole structure, and these deformation should be within the elastic limit only. So if you cross this elastic limit, then the load cell is going to damage. So at these samples, they're going to give the elastic strain gauges. They're going to keep it. So these elastic strain gauges will calculate the strain along these portions out of all these kind of arms actually, and then give the average displacement of these arms. So because we already know what is the sample geometry, load cell geometry, and also we know what is the elastic modulus of sample. In the deformation load cell, basically elastic limit, load and the deformation within the elastic limit. The load is directly proportional to the displacement. So the load is directly, and it's basically linear relationship. So if you know the displacement by measuring the strain gauge, then you can calculate the load by just simply substituting the proper geometrical factor and proper modulus. So from there, actually indirectly, basically you're calculating the load of the sample. And the load cells can be calibrated in a frequent intervals of times. Basically, by manually can also calibrate by putting some loads and measure what is the output velocity, output voltage, and see if there is a linear relation is existing between the loads and the output voltage, and you can calculate whether it's can basically generate a curve also. So basically, this is how the load cell works. For example, if the material, if the load basically by any chance in the machine exceeds the elastic limit of this sample, then there is some permanent deformation will happen. Once this material going to permanent deformation, this strain gauges are going to get damaged. And once the strain gauges are going to get damaged, then what are the results you're getting? Erroneous results. So that means the load cell is no more useful. So I have to always make sure that the output load of any mechanical testing machine should be below the elastic limit of the material. That means below the load cell capacity. So this is how the typical stress strain curve looks like of a mild steel. This is generated from the literature, from the internet. So this is how this basically there is initial linear part, and there is a increasing the load, and then the yield drop will be there, and then again there is a plastic deformation will happen by further increasing the load, strain hardening the material. So this is people call as elastic deformation. This people call as elastic deformation, and this is basically is called yield drop. This is the upper yield point, this is a low yield point, and this yield point elongation will be there. This kind of yield point phenomenon will observe only in some specific type of materials, mostly in the steels, or if the materials where there is a some amount of interstitial solid solution, because these interstitial solute atoms will go and precipitate along the dislocations to reduce the dislocation energy. So when you apply the stress, the dislocation has to break the solute atmosphere and then move. Then only you get the plastic deformation. But to break this solute atmosphere, we need a more stress. Once the dislocations break the solute atmosphere, then the stress decreases drastically. And then further deformation takes place by strain hardening, which is a typical mechanism of interacting the dislocations and all those things, which is responsible for the strain hardening behavior. So this is basically the stress at which the dislocations break away from the solute atmosphere. So this, to observe this thing, people should the material should have some interstitial solute atoms, or sometimes people observe in the substitution solid solutions also. This kind of behavior people see, but in general pure metals you won't see the solid solution. This ill-defined phenomena. Even in steels also, you apply significant significant amount of cold work. Then you do the experiment, you won't see this ill-defined phenomena. Okay. Then if you come back to the curve, so basically this is called elastic deformation, and the slope of this curve gives the elastic modulus. And then here basically you can get the proportionality limit up to which the stress is proportional to the strain, and then is basically a elastic limit beyond which you see a permanent plastic deformation, and then you see a maximum UTS where there is instability will happen. Instability because here this all basically engineering stress strain curve, right? The engineering stress strain curve means basically you are calculating the stress based on the initial cross section area, but the cross section area of the material is different, because the cross section continues decreasing because deformation is happening. At the same time, the material is going to strain hardening. So one side the material is strain hardening, so that means the load required for further deformation is increasing. Another side the cross section is decreasing, so that the load experienced by the machine is basically increasing. These two will actually the opposite direction, and at some point these two will balance, where further increasing the stress decreases decreases the for the load of the material, decreases the stress actually. This is called low instability, and this is the stress at which this instability happens is called the ultimate tensile stress, and further the stress basically decreases. This is how the typical, and then the area under curve up to this point is called modulus of resilience, which is very important for shock absorbers, people who have materials applying in the shock absorbing, like for example bumper bars and all those things. And the area under this plastic regime, this curve is called toughness. This is the energy absorbed by a material before fracture. This is very important property, and the notch fracture toughness is much more better engineering property as compared to tensile fracture toughness. But whatever it may be, the fracture toughness is very important. To get a good fracture toughness, not only increasing the yield strength is important, because you have to get both strength at the same time. We have some amount of ductility can give a better toughness. That means we should have some good strength at the same time some amount of ductility. That will give the good fracture toughness, good toughness. So these are basically engineering stress strain curve, and then you can convert to true stress strain curve using these relationships. But these relationships were derived under the assumption of the constant volume, because plastic deformation is a constant volume process. Elastic deformation is not a constant volume process, but plastic deformation is a constant volume process. So when constant volume is, for example, after this yield stress, after this UTS, when the neck is forming, where there is a triaxial stress that is there at the neck, and then where the voids will be generated in the neck, where there is a basically cracks can be generated in the neck, then this constant volume will not hold. So these relationships will be applicable only up to UTS. Beyond UTS, we can't basically use the relationship to convert the fracture strain of engineering fracture into true fracture strain. You can convert UTS, engineering UTS to true UTS, but you can't use the fracture stress strains by using this relationship because constant volume will not hold. So now this is basically the OFC copper which is developed in our lab. OFC copper, OFC means oxygen free copper. Oxygen free copper we taken, and then we made a tensile dog bone shape tensile sample, and then we applied a stress and strain, this engineering stress strain curve. And basically this is basically the slope of the curve. There is some problem during the test, but this is actually the elastic regime, and the slope of the curve basically gives the modulus. And you see what is the modulus of the machine is around 32 GPa we got from this slope. But what the modulus of the copper, if you see the literature, that is around 126 GPa. Why this discrepancy is coming? Because the displacement what you are getting, from which you are getting calculating the strain, is basically the cross-side displacement. If you go back to this stress strain curve, this uniaxial machine, basically you are getting the displacement of this cross-side, which includes basically the strain from the sample and the relaxation in the grips, and also some amount of elastic deformation of the grips, and there is some amount of the elastic deformation of the pull rods. All together will basically come into the this cross-side. So all these strains will come into the cross-side. Basically, load. This is the basically strain is what the final change in length by initial length. The change in length is much higher than the change in length of the actual sample. That means your strain is much higher than the actual strain of the sample. So your modulus is basically stress by strain, because your strain is much higher than actually strain. So the total ratio decreases. That's why modulus actually decreases. This is actually very, very important to see whether the strain on the sample you measure manually and the strain coming from the test is to matching or not before going to make any validations of the sample, before going to make any conclusions of the data. So how to correct this one manually? If you don't have any sophisticated equipment, so still you can correct this. This is called compliance of the machine. Machine compliance is also included in the test. So how to neglect the machine compliance? One way is that you use for example, compression experiments, take the sample out, just compress the sample with plate ends. So with the plate ends, so that means then you generate a curve without sample, which is basically includes the relaxation from the sample at the different loads. As every load corresponds to seeing the displacement. This is what's called mission displacement, basically from every load. Then this is basically your test data, including mission components. For every corresponding load, the displacement from the machine is subtract from the displacement of the total sample, total displacement of the cross section. Then basically finally the displacement what you're getting is basically displacement from the machine from the sample, which is a true displacement. Based on that, you can calculate the strain. That is basically gives a true strain or true engineering strain of the sample. So using that one, if you do it, that will be like different from the basically if you see here, the displacements are much less, significantly lower than the displacement from the cross-side velocity. So this is basically how you do the manual compliance corrections. But this may not, nowadays people are not going for this manual correction. Most of the machines have its own software which can build, generate this curve and give the curve to the software. It will do the compliance correction automatically. Instead of measuring the cross-side displacement, can we measure the sample strain directly on the sample? If we measure the strain directly on the sample, then we exclude the strain coming from the displacement coming from the relaxation of the grips, relaxation of the loads, the deformation, elastic deformation of the pull rods, push rods, and all those things. That means that you are calculating the true displacement of the sample. How to do? You can do using extensometers. You can actually calculate the true displacement of the sample. Actually, to measure the displacement directly on the sample, it can exclude the displacements of the from the relaxation of the load train. No machine compliance correction is required. So different strain gauges are the extensometers are there, which is elastic strain gauge, which where they keep the elastic circuit on the sample, they will paste it so that this elastic circuit increases its length while deformation is happening. So increasing the length, the resistance changes. So the final output current voltage will change, signal will change. From that, they can calculate the strain on the sample. Or you can use the laser extensometer, where they put some kind of interference pattern on the sample, and you basically project the laser on the sample, so that whenever there is a contrast from the changes, there is echo you see in the screen. of the extensometer. So different distance between the two echoes you can calculate. From there you can actually calculate distance on the sample. And there is high temperature extensometers are there, and also it's called digital image correlation. So digital image correlation is getting more and more popular because you not only get uniaxial strain field, because you can get a 2-dimensional strain field on the sample. So you can do much more better analysis of the deformation behavior as compared to the linear elastic extensometers. So just I'm going to talk about how to measure the strain using digital image correlation. You can consider this is extensive in situ tensile tests actually you can consider. So here what we do. Hello? Yeah, right? Everything is okay?
Sir, yes, sir. Everything is okay, sir.
Yeah, fine. I keep asking in between. Sorry.
Yeah, no problem.
So basically, this is how you are doing a basically DAC. DAC basically this is a dog bone sample. Forget about this green color. This is software. We try to put some contours on that. But this is how the sample looks like. We are putting a speckle pattern. Speckle pattern means basically we have to create a contrast image on the sample. For example, there is a white background. You are giving a dotted pattern on the sample by spraying a black paint you will spray. And then in the process, you get great at white and black contrast you create throughout the sample. If the sample itself is having some kind of contrast difference, then you can directly use the sample itself. If there is no contrast in the sample, white black contrast is not there. Basically, then you have to paint the white paint first. Then you have to paint the dark spray so that you can create actually this kind of speckle. This is called speckle pattern create on the sample. This sample, you keep it here. This is basically the tensile Instron machine in our lab. So basically, then there is a flashlight and then there is a camera. Then you can, every frequent intervals of time, you will record the images of the sample during the experiment. So you're applying the load for every frequent intervals, every interval within the interval, you are collecting the image. At the same time, you are acquiring the data from the load cell into the machine. So the load cell information you're getting from the machine, and these images you are getting from the camera. And then this is basically high temperature DAC, where this is a furnace is available. We already furnace is there. Sample is inside the furnace, and there is a quartz window we incorporated in the furnace, through which we can actually focus the sample, and then we can get the images during the deformation. These experiments were done at 700 degrees centigrade. So when you go to high temperature DAC, the paints we have to use the high temperature paints to use so that the paints should not decompose or evaporate at that temperature. So this is how the sample speckle pattern looks like. Okay, I'll give a very brief methodology how they calculate the strain from the DAC list. Okay, so for example, this is a whole region. For example, if you choose this area, you want to correlate. Once the test is over, then we'll take all the images into the DAC software, where they'll choose the basically your area of region of area of interest. In that area of interest, for example, this is your area of interest. This subdivide the whole area into subsets. This is called subset. Okay, this is called subset. The whole area is divided into subsets. Okay, each subset at least contains minimum 10 speckled dots will be there. This is how the subset, the dots are there. This is a dark contrast. This is a white contrast. The gray scale of the dark contrast is around 250. The white contrast is around 256. Right. So this is how the contrast difference is there in the gray scale. So these are the subsets are there. These subsets you will basically divide, and each subset should at least get a minimum 5 to 10 spots should be there in each subset to get accurate results. So for example, this is one subset is there. So basically, whenever there is a black, you get a 0 grayscale. When there is a white contrast subpixel, these are basically pixels. These are pixels in a subset, right? The white pixels basically give the 255 contrast, and the dark pixels have the 0 contrast. That is the reason we put a white and black background so that there is a clear distinction between the grayscales. So after deformation, this sample will move. That means basically then in the same area, if you consider, then the subsets are different, because here this part initially the dark pixel is there, now it becomes white pixel is there. That means if you compare this one with this one, the subset is not same. Okay, for example, this is the correlation function it's called, because this is the intensity of all the pixels in this subset. And this is the intensity of all the pixels in the subset. So what they do is basically once you apply the correlation function, these subsets will compare with it will have a scan. For example, the subset will go first here, then you'll compare next, then you'll compare next, then you compare next with some step size. So in each step, it compare what is basically the intensity of that subset. So the intensity of the initial subset and this is the intensity of the final subset. If these two subsets are same, that means the correlation function you get a 0 value. That means it's perfect match is there. That means the subset is moved from this place to that place. For example, if you see here, the subset is moved from this place to that place. That is what you consider. Then the x and y displacement we can get. What is the x and y displacement to move this subset from this subset to this subset? Basically gives you a displacement of the subset, displacement vector basically in the two-dimensional field. Okay, so like that it compare for every subset, it compare, and then what is the UV values? Basically, this is the basically displacement vector for every subset it can record. That means how the displacement of each subset is basically changing, it can record. Okay, like that. So like that, sometimes what happens in the subset is this is the initial subset. Then the subset can change its shape also, because the strain also when happens, the subset itself it can change the shape. That also incorporate in this correlation function by using suitable algorithms. In that process, finally get a two-dimensional strain field of every point. What is the xy displacement? What is the y displacement? You can record by using this for every image. So every image they compare with the initial image and then get what is the u and v displacements of that every point in that particular image. Like that for all the images it will calculate. Okay, this is how the structure uniaxial compression experiment, how the deformation is taking place. See, there is a deformation happening. All the pixels are moving during the deformation process, and then each image. These are basically the collage of all the images and make a video. Okay, so each image it actually gives the correlation function and then calculate the x and y u and v displacements of each pixel in each image, and then it actually calculate the strain. For example, this is the strain of the EYY. Basically, here what I'm calculating basically what is the every pixel, what is the what is the EYY strain basically, and based on this is the scale basically color coding. Means -12 means basically it's compression, +2 0.2 is basically it's tension. So when there is this is compression experiments, right? So then how this is actually evolving during the experiment you will see. See, this is how it's happening. See, this is basically how the deformation field is actually. So this is how two-dimensional strain field. With the extensometer only we can get a uniaxial strain, but here you can get a two-dimensional strain field you can get. So you can do much more analysis in the deformed material, deformed sample. So basically, for example, here you are seeing some amount of tensile stresses you are seeing because there is a frictional stresses that generated from the surface. Then here you are seeing more axial tensile compressive stresses are there, which is 45 degrees to the tensile axis. That's what generally we expect because the resolved shear stress along the 45 degrees is much higher. That's why the shear more happening along the 45 degrees. That's why here at these places you are seeing much more compressive stresses you are seeing along this direction. Then now how to calculate? Basically, for example, now at each point of the stress strain curve. For example, this is the uniaxial strain, the overall strain, they calculate in the x-axis, they have stress input from the y-axis. Together we generate the stress strain curve. Now, at each point, how this contrast looks like. For here, it's completely uniform is there. It also strain, not much changes there. At point 4, there is some amount of strain you are seeing along this pattern. And then basically around 0.5, you see much more strain. And then increasing the strain, the strain is much more inhomogeneous and more strain is concentrated along the center 45 degrees along the tensile axis to the compression axis. You can also do much more things. For example, how the strain along this line, along this line, along this line, and along this line. For example, this is correspond to this red line, where if you see here as a function of the y of at 0.012 strain, means this is the 0.012 macroscopic strain of the sample. How the strain distribution is there along this direction, the strain distribution is much more uniform. But along this direction, there is a deep peak in the strain. Basically, here more compression, basically compression strain, and here not the strains are much lesser. So the strain is much more inhomogeneous. In this way, you can see how the strain feels during the deformation, and it can be possible only with the DIC, digital image correlation. And this is basically not only in the line, we can also create particular points how the strains are there. For example, here this is at the strain of 0.06 maximum strain. This is how the strain distribution is there. For example, here if you take here more tensile part is there, and if you take here, for example, here more compression part is there. So this is how the strain distribution also you can see at each point also you can calculate. So you can see, for example, it's a two-phase microstructure. Each phase how the distribution is strain actually partition you can calculate. For example, we have very coarse microstructure length scale, two phases there. So the coarse, the hard phase how the strain partition, and the soft phase how the strain partition. The strain partition how is happening between the hard phase and the soft phase you can calculate from this mechanical testing machine. Hello, how much time I'm having?
Sir?
I can take my at least 45 minutes more is all right.
Yes, sir. Yes, sir. If you want, we can take 5 minutes break also now.
Okay, this after this section is over, then we'll take a break. Is okay?
Yeah, okay, sir.
Okay. So then this is basically this is the uniaxial stress strain curve calculated from the displacement from the crosshair that we just showed at the initial slides of my presentation. This is the stress strain curve I calculated using the DAC which I showed just now. So this is the two different length scale experiments are there, and I calculated the modulus by calculating slope of this line and modulus slope of this line. The calculated modulus on the cross sector velocity is around 32 GPa, and the calculated modulus from the DAC is around 118 GPa, and the actual modulus is 126 GPa, and which is actually suggesting that the DAC is giving much more accurate value, and you have to validate also for every time. So suggesting that the accurate value of the modulus as compared to the cross sector velocity displacement. And not only that, the fracture strain also can changes, and then with the strain at which correspond to the maximum stress can change. All those things will change when you calculating using DAC as compared to the cross velocity. So for every tensile experiment, it should be important to calculate the what is the displacement from the mechanic machine test machine and what is the displacement from the sample after the fracture, and you to see whether these both are comparable or not before making any validated conclusions. Okay, now I'm going to instrumented depth sensing harness. So we'll take some break now, like 5 minutes.
Yes, sir. Yes, sir. We can take break for 5 minutes.
Thank you.
Thank you, sir.
Let's start now.
Yes, sir. Yes, sir. Please share your screen, sir.
Again, I'll share it. Okay.
Yeah, yes, sir.
You got it?
Yes, sir. Full screen. Now it is in small screen, sir. Yes,
No, it's
sir.
fine.
Yes, sir. It's fine, sir.
This instrumented, that's what you're seeing, right?
Yes, sir. Instrumented depth sensing hardness.
Because here many windows are open. That's
Yeah. Okay, sir.
close this one. Okay. Okay. Thank you. Thank you for the break, and then we'll come back. So
So now it is showing another slide, sir.
no,
Now it is showing mechanical testing further classification slide.
but then something is wrong.
That is 10th slide.
Then what I'm seeing is different from what you're seeing.
Yes, sir.
Let's close it and I will share it also.
Yes, sir. Now the slide is okay, sir, but it is in small screen.
Okay, now slide is seeing, right?
Yes, sir. Instrumented depth sensing hardness.
Now it's fine.
Yeah, but it is.
Yeah. I'll do it. I'll do that.
Yeah.
Now it's fine.
Yes, sir. It's fine, sir.
Yeah.
Thank you, sir.
So in this particular section, what I'm going to discuss is that, so what is the difference between instrumented depth sensing hardness as compared to the conventional hardness testing? Basically, hardness is nothing but it's basically a resistance to plastic deformation. It is another way of measuring the strength of the material, right? So basically, in tensile test also you do the plastic deformation and you get the stress response. In hardness also you do indent it rather than a deform actually you do indent it and see how good the resistance to the plastic deformation. If the more resistance to plastic deformation, then it's more hardened material. Less resistance to plastic deformation is less hardened material, basically. Okay, this is why we have to do this micro hardness scale first of all before going to the length scale. Because, for example, take a length scale of any microstructure. This is basically all these pictures I get it from the internet. So this is basically the copper is what we are by copper piping. And if you see the optical microscope, this is how the grains are looks like. It's basically in the micron length scale. Then if you go to TEM and then seeing each grain in that, you get a sub-grains basically. These are not grains actually. These are the grains and these are the grain boundaries. In this each grain, you see sub-grain network. Means basically these are called dislocation dense region and these are called dislocation less dislocation density region. So this is called cell size. There is some amount of deviation, orientation difference will be there, like 1 or 2, 3 degrees centigrade. But this is not actually high angle grain boundaries. And if you go in the TEM, then you see the dislocations actually. And these are the dislocations, how actually moving along this particular direction. These are the grain boundary, how the dislocations are coming there, and then how the dislocations are coming there, and then piling up ahead of the grain boundary and all those things. And if you go further magnification, the TEM, and you see basically the HRTM. Here basically the each contrast dot white contrast basically represents the each atom actually. It's not a one-to-one atom, but it's basically each white contrast basically can consider the representation of one atom. So here you can see how the actually atoms are basically aligning there. If you see that this sign basically called dislocation, edge dislocation. So you can actually see edge dislocations are actually aligning along the grain boundary. Basically, this is one example of the low angle grain boundary, and they calculate the distance between the dislocations, and then using the theta is equal to b by h. B is the Burgers factor, and they can actually calculate the orientation difference between the two grains. This is a classical class book formula. The how to get the orientation between the two low angle grains separating the low angle boundary from the spacing between the dislocations, right? And this is how the length scale is there. On the top of that, there is a pure material is there, where all the grains are having the same phase, and there is a two-phase structure is there, where each one, the composition and the crystal structure partition, the composition partition of the two phases will be different, and also the crystal structure of the two phases will be different. Then the mechanical properties of the two phases are different, and you apply a macroscopic load. The strain partition between the phases can be different. To model the macroscopic load, you should know what is the individual mechanical properties of individual phases that you can't do in a conventional uniaxial tension machine, right? So then you should know what is the hardness, what is the modulus, what is the load displacement data, if at all possible, of each individual phases. Then you can use in the crystal plasticity model, and you can generate the macroscopic crystal plasticity, much more representative stress strain curve of the macroscopically, using crystal plasticity or FEM analysis, right? So these all is very important, which is not possible in the conventional mechanical testing machine. And if you do, then can we do with the normal indentation? Basically, this is a macro indentation testing, which is generally people uses. There are different indentation techniques are there. First, indentation can be classified, hardness can be classified into three different things. One is basically scratch hardness, I'm not going to talk about. And then is a dynamic hardness, rebound hardness, that I'm not going to talk about. And third one is the indentation hardness. Indentation hardness, where they take a material, and then this is the material, and then you indent it through a tip. The tip can be a different geometries depending on what kind of indentation technique you're using. And then we see the either basically the indent cross section, the area, projected area of the indentation, or the depth of the indentation after you remove the load. So if you're using a spherical conical indenter, and then use the depth of, based on the depth of the indentation, you can actually calculate the hardness in the Rockwell hardness tester. Or using spherical indenter, and after indentation, what is the size of the indentation impression you can calculate. From there, using expression, you can calculate Brinell hardness number. In the similar way, you can use a Nuke hardness, which is basically micro indentation technique. Or you can use using Vickers hardness also, you can calculate from the projected area of the indentation. Load divided by the projected area, you can calculate the hardness. These are the different techniques. Brinell, Rockwell, and Nuke, and Vickers, all these are different, and Mayer's hardness test is there. All these are different macroscopic or microscopic hardness techniques. But these techniques will only, the output is basically the indentation depth or indentation, the impression diagonal or diameter length, that either the diameter of the indenter or the length of the diagonals. These are the only things we can available, but we don't know what is happening during the indentation process. This is called conventional hardness testing machines. So the residual impression diameter or size are the measure to calculate the contact area. Using that contact area, calculate the hardness, and the penetration depth not taken into account during the indentation process. So how it is different from the conventional nano indentation technique? In impression, this is basically it's called nano indentation. It is called a depth sensing indentation, or it's called a instrumented indentation test. What it does is basically it gives the load displacement response during the indentation process. For example, doing the indent, basically this is not possible 20 years down before 20, 30 years. But now, because the precision of measurement, the low loads, fine loads are very important, very much available, the techniques. So this technique could possible. So what happens, basically you do the indentation particular depth, and the response load you will actually measure. So that's what we are doing in the conventional mechanical testing, right? Where you're applying the load with particular displacement, right? And then you get the load response, right? So here also we apply with particular load displacement, and then you record how much load is actually getting from the sample, and this we calculate. This is basically increasing the load with increasing the depth. Then it's the maximum load or maximum depth depending on what actually you're giving, and then there is a unloading curve. Right, this is unloading curve, and this is basically sometimes what happens, they'll hold the load at some time at maximum load for some time to see whether there is a creep, some kind of deformation happening or not. And basically here one thing you observe is basically the unloading curve initial part is basically linear part, which suggesting that when the unloading is happening, first relaxing is basically elastic recovery is happening. After the elastic recovery, there is a permanent plastic deformation is there. So this is basically the permanent plastic deformation. This is basically the elastic deformation. Basically, this is an elastic deformation you can consider, but no need to worry. This is basically an elastic deformation. This is elastic recoveries that are happening basically. So the slope of this curve basically gives some kind of modulus. What modulus is called? Reducer modulus, because this modulus consists from the low indented tip, because indented tip also can deform, and also it can do basically elastic recovery of the material with which you are indenting. These two actually two basically actually the included in the slope of this curve. This is basically the reduced modulus, and this is basically the elastic. After this elastic recovery is happening, this displacement basically give the HC, that is called the depth of the indentation after elastic recovery. This from this you can calculate from the HC, and there is a shape function you can calculate. This shape function, for example, particular geometry, I will show you. Meanwhile, I explain. You can use Berkovich, different geometry tips you can use. For each tip, there is a particular shape function is available. But that means which can relate the some constant with the depth of the indentation. For example, you have to multiply that constant with the depth of the indentation. You can get the what is the basically projected area, right? So the only assumption that the shape of the indentation is constant. The shape of the indentation should be intact. It should not change the shape of the indentation. Sometimes there's no varying of the indentation, nothing happens. That means the constant value multiplied with the HC can give the basically projected area. Basically, you can calculate, right? So this is basically how the elastic deformation happening, and this is again the same thing. This is basically the HC thing. We have to calculate HC. Measuring hardness, I'm using all of them, right? This is how the indentation in machine looks like. This is basically Hyzitron machine which we are having now. This is basically the optical axis. This is the indented transducer which is having the indented tip will be there. Basically, this is the transducer. In the top below the transducer, we'll see the indented tip. This is how the indented tip is a small tip you are looking like. On the top, this is an indented tip will be there. That indented tip is going to the penetrate into the sample basically. First, what to do is first this optical axis will be sample will keep it here. The optical axis will come in here and then see the sample and you find out the place where you exactly want to do indentation. Then this optical axis, then you ask the machine to take the indenter, the transducer come there. So this optical axis will go. That's the sample stage will go move towards the transducer, and the region where you selected actually you're going to indent it. Okay. So once you indent it, the first the load will apply and then unloading will come. Then the typical loaded unloading curve I showed before. Then from there you calculate the hardness, right? So how this basically the why is possible to measure the displacement and load? Because the load is basically the measuring by using a 3-plate transducer. The different companies using different techniques to measure the load, because you have to sense micronewtons, right? And nanonewtons, micronewtons you have to sense, because sometimes the load capacity of transducer is 10 millinewtons. That means your loading sometimes happens in micronewtons also. So what they do is the 3-plate transducer, and the moment on the transducer will give basically the linear relation with the jet position of the transducer. So if it is more there, that means more you can get the more output. From there you can actually calculate what is the load. At the same time, the position of the indenter also can calculate either using the LVDT, linear variable differential transducer, or by using laser. So here, for example, this is the material, right? For example, if the material is going up and down, this tip is going to move up and down. When this tip is moving up and down, you are putting the laser, right? And this is your reflecting the mirror and then forming the scale. When tip is moving, then the reflection displacement will change. From there, actually calculate how much actually this one will move up and down. And this is a technique people uses in even AFM also in the contact mode. And the linear variable differential transducer also LVDT also uses to measure the displacement of the tip basically, because you need two outputs. One is load and there is displacement of the tip in the downward direction. So basically this is having the LVDT, and mostly meteorological people might be knowing how this actually works. This is a primary coil and this is a secondary coil, and there is a basically the core will be there between this one, and this basically connected to the tip or whatever it may be, to where you want to measure the displacement, and some movement is there. This core will move in this one. Then the number of secondary turns cut by this core will change the movement of the internal core. That means the output also, the secondary output also will change. From that you can actually calculate how much this movement is there. From there you can calculate how much the movement of the tip is there. This is another way of measuring the displacement of the tip. So once you know the displacement tip how it's moving, and also you can calculate the how much what is your hardness, then you can actually generate the load displacement data. This is what are the different kind of tips that you uses for the nano indentation machine. One is basically Berkovich tip, which is very widely used tip, and this is basically cube corner tip. Cube corner tip is basically a corner of the cube you can consider. So basically this is 90 degrees. These are angles at 65 degrees. Or another widely used machine tip is basically Vickers tip. On the top there is spherical tip is there and the conical tip is there. This is how the impression of the tip looks like after indentation. So how the spherical tip is different from Vickers and Berkovich is that the Vickers basically the the strain that inducing during the pump, because when you're pushing the material indenter into the material, it creates a strain field in the material, right? The strain field directly depends on the tip geometry. For example, if it's a Vickers or a cube Berkovich, this is called self-similar indenters. That means once you decide the angle of the tip, that means the kind of strain imposing into the material is constant, independent of the depth of the indentation. How much deep you go, that much indentation only, that much strain only you can induce. But in the spherical indenter, by the strain is directly proportional to the A by R, where is A is the impression diameter and R is the spherical diameter, the diameter of the indenter. So based on that ratio, your strain is continuously increases with the increasing the depth of the indentation. And the cube kernel generally induces huge amount of strains even for a small amount of displacement at depth. This because of the sharp tip. Generally, they use to calculate the fracture toughness, where because of huge strains, it creates cracks along the corners of the impression in a brittle materials. The distance of this crack propagation, from that you can calculate the fracture toughness. For that, we use cube kernel indenter. So the geometry has own purpose. So in general hardness measurements, people use this because you want to basically nullify the effect of the strain. You want to maintain the same strain in all the indentations, right? Then you use the Berkovich and Vickers. For example, you want to measure the particular property as a function of the strain. Then we use the spherical indenter. But generally, there is a techniques where you can generate the stress strain curve from the indentation depths and low displacement data of the indentation. So there you have to change, the strain has to change continuously. In that cases scenarios, you use the spherical indenter, and of course measure the fracture toughness, you use the cube corner indenter, right? So now how we calculate the load? Basically for Berkovich indenter, as I mentioned already, for a particular geometry, this is constant is same as long as the shape of the particular tip is intact. But which is not the case. During the process of using, the shape also can vary. That we'll discuss in a meanwhile. Okay, this is basically HC. We can calculate from the machine. Once you put the HC into A, you get the projected area. Once you get the projected area, apply load to projected area, basically you get the hardness, right? And also we can get the basically we get the from the slope of the curve of the unloading curve. Generally, the initial part of the unloading curve, we can get the reduced modulus. The reduced modulus can be equated to the 1 minus Poisson's ratio of the sample by Poisson's modulus of the sample specimen, and also 1 minus Poisson's ratio of the indenter and Poisson's ratio of the modulus of the indenter. This we know. We can make a reasonable assumption. Then we can calculate the modulus of the sample. This is how we can calculate the modulus of the sample, right? So this is how you can get the S is basically the basically same thing I mentioned here. You get the modulus, and you can get the reducer modulus by using the shape function, and then this one, and you can get from the hardness, you can get the Pmax by A, and the same thing I'm repeating here. Same thing. In principle, you can calculate the modulus and hardness of a particular region. Another advantage of micro tensile nano indentation is that sometimes these days these thin films are very popular. Hello, is okay everything?
Sir, everything is okay, sir. You can go ahead.
So another advantage of nano indentation which I mentioned here is basically these days thin films are very popular, where the thickness of the film is in the order of micron, sometimes in the nanometer also, right? So when you're doing a normal indentation or high load indentation, the strain field of the indenter, because when you put the indent, right, then put the indenter into the material, it creates some strain field or stress field. The stress field will not only penetrate into the thin film, but also penetrate the substrate. So the water final properties you're measuring is basically together of the combination of the both film and the indenter on the substrate. So if you go to low loads, that means you can measure only the strain fields only confined to your film only. Then you can measure the properties of the thin film without interfering the substrate, right? Without interfering the substrate. At the same time, you'll see meanwhile, we can't further reduce the size of the indent without any, you can't keep on reduce the size of the indent, because you can confine the stress field only to the thin film, because there is a size dependence. Size indentation size is going to come into picture, which I'm going to discuss in a short while. Okay, so the another advantage of the nano indenter is to measure the thin films. That is the I want to bring it to you guys notice. So what all things you can measure is the nano indentation. One is basically, of course, you can measure this is how the loading function will be there, increasing the load, maintain constant load, and then decreasing the load. This is how the Berkovich impression is basically after the load, after the unloading. And this is a stress strain curve. You can actually calculate the hardness and modulus. On the top, you can also apply a sinusoidal function because there is a load. On the top, you're applying a sinusoidal function. Basically, means the increasing load, decreasing load, some kind of with particular 10 to 20 micronewtons kind of that kind of oscillating load also you can apply. From there, you can actually calculate the stress strain response. This is not that one thing is we can calculate the modulus, and second thing is basically is very important in the viscoelastic materials where the stress to strain response. For example, the metals, you apply the strain, you can immediately get the stress. So if you plot the function of time, the stress and strain, the both curves will be collinear one on the other. But if you go to viscoelastic materials, when you apply the strain, the stress will follow after certain amount of time, right? So the maximum strain it reaches after some amount of phase difference. The maximum of strain it reaches after some amount of time phase difference. The maximum stress will come. So that means there is a difference. This is because this is a property of the viscoelastic materials, which is very important for the polymers and soft materials, right? So from this you can actually calculate the tan delta. This is called loss modulus, which is a very important factor that we can calculate using this oscillating force using DMA. This is dynamic mechanical analyzer. Because and also we can actually scratch the sample by using the indenter, and actually we get the wear properties and the wear properties of the thin film and all those things. On the top, as I mentioned earlier, this is a cube corner indenter. When you cube corner indent, you hit the substrate, it generates a cracks if it's a brittle material. If it's a ductile material, it deforms plastically. If it's a brittle material, it generates a crack. So these cracks, if you measure the crack length, from that you can actually calculate the fracture toughness. Though this is not a well agreed way of measuring the fracture toughness, at least it can give it quantitatively to measure the fracture toughness. It can also sometimes helpful to create the fracture toughness of individual phases or in a thin film or locally particular length scales. You can measure the fracture toughness. On the top of this thing, new technique is developed where you can actually calculate the current during the deformation itself. This is the displacement, and this is basically you're getting the current. What is happening is basically when there is sometimes what happens when deformation is happening, when huge strain fields are creating, there is sometimes happens deformation induced phase transformations. Sometimes the phase itself will change. Sometimes springs will nucleate. Some kind of things can happen during the deformation process, during the indentation, and this it can change the local resistivity, which can pick out from the current signal. So from this nano ECR, we can actually calculate the basically at which strain, which depth, we can actually get the deformation induced phase transformation. This also you can calculate from this nano indentation measure. Sometimes you can use the high temperature by heating the sample. You can do high temperature indentation also. You can measure at the function of temperature of the indentation of individual phases is changing. You can calculate, and this data you can input into the crystal plasticity modeling, and you can actually calculate a more qualitative, quantitative way of calculating theoretically the stress strain curve of a particular two-phase material. And this is one way we have done in our group. This is basically a high entropy LI, and we saw the grain boundary we are seeing right here, and we don't have any technique for us to see the chemistry of the grain boundary is changing or not. Then we thought what can be indirect way of calculating during heat treatment, whether there is a solute atoms are precipitating here. One hypothesis is that the solute atoms are presenting here. The solute atoms are dissolving into the matrix at high time, at a different annealing time, the annealing period. Like for example, if you do 1050, the solute atoms are presenting here, and 1100, we are expecting that solute atoms are dissolving into the material and actually increasing the stacking fault energy of the material, which is very important for the strain hardening properties and all those grain size and pinning and all those things. But we don't have any technique to measure the composition locally of the grain. So what we did is basically initially we take a sample and we choose a particular grain boundary, and we see the hardness across the grain boundary, and this is the grain interior, and this is the grain, and this is the sample which is annealed at 1050 degrees centigrade for 4 hours, and they see how the grain, the indent hardness in the grain is around 4.4, and that the grain boundary we've done more experiment, more indentation in the grain boundary, and the hardness is basically around 5.5 or something like that. And again, other grain the hardness is down to lower hardness, right? And then the same material we heat it to 1100 degrees centigrade for 1 hour and see what the hardness is there. So then we see the hardness at the grain boundary is equal to the grain. So what hypothesis we could get from that is that there is a chemistry of the grain boundary is changing during the annealing at 1100 degrees centigrade. That's why the hardness or the grain boundary is also dropping. This is the indirect way of saying that there is a dissolution of the elements, second impurities from the grain boundary into the matrix, and then these impurities can precipitate along the stacking fault planes and reduce the stacking fault energy. This is a way of indirectly dealing the stacking fault energy, find out the what is the grain boundary chemistry, what is happening, what is the grain boundary hardness structure is changing, evolving during annealing and other deformation processes. This is another advantage of this nano indentation machine where we use it. So this is another thing. We basically, this is silk thin film. Silk is very soft material, right? In the silk film, very thin film. Also, we basically they deposit the silk film from the silk and they do some processing. And this is I work with Professor Sivaram Krishna along with me. He's actually working. He's collaborating with me, and we actually calculate the hardness of this silk film, and we observe around 0.2 or 0.25 as the average hardness. It is independent of the depth of the indentation that we could see it actually. So what kind of, while doing indentation, though it's giving a very advanced information of particular phase, particular material, particular grain boundary, but unless if you're not careful about enough, then it can create very erroneous values. First thing is basically thermal drift. Hello, is there? Hello.
Yes, sir.
Yeah,
Yes.
yeah, yeah, fine, thank you. So first, oh, start. Shit. What happened?
Last your screen shares.
Yeah, I don't know. I didn't see my screen also.
Yes, sir. You
Just
are also
1
not
minute.
seeing your screen.
Please give 1 minute, please.
Okay, sir.
I think something I touched it. Now see?
Yes, sir. But it's in first slide, sir.
Yeah. It's taking a lot of time. I don't know, this is not a problem. Internet problem. Not enlarging. Something happened. sorry.
No problem.
Some technical problem is not. I didn't touch something. Is happening. Some internet problem. Seeing right now?
Yes, the first slide. We can see first slide, sir. But in a split view, sir.
Yeah, the first slide to come to the. This is also not. It's getting stuck actually. Sometimes it's not working.
Yeah, okay.
I don't know. Somehow it is. This display settings is not appearing here.
But we can see it from here, sir.
Yeah, you're seeing that it is not happening working.
Yeah, there we can see display settings. Now
Yeah,
your
but
pointer is on.
yeah,
Display.
now it came. Now it came. Now it came.
Okay, sir.
Let's, it's not allowing to. It is inactive actually. Can it be present like this? I don't know. Honestly, waste of space. I will log out and come back for 1 minute. Okay, please.
Yeah, okay, sir. No more. No problems.
Yeah, participants, we have a small technical glitch. We'll just be back.
Yeah, now fine, now fine. And we actually unmuted somebody actually. Disable participation sharing window.
Now you can try, sir.
Now you can try, sir.
Host disabled participant screen sharing.
Now we enabled it, sir. You can try it now. Can you do it, sir?
No.
Pradeep sir, Rajesh sir is not co-host. Making co-host so that.
Okay.
Yeah, now I can do it.
Yes, sir.
You can see now, right? Hello?
Yes, sir. We can see it, sir.
Yeah, whole image you can see, no?
Yes, sir. Now it is more.
Yeah, done. So they can take some few slides are there. I promise I finish early. Let's see. Okay. Hello? Can I continue?
Yes, sir. Please, sir.
Yes, sir.
Yeah, actually, this nanoindentation, though it's giving very advanced information of a particular material, but it can give you a lot of erroneous data also if you're not careful. First thing is basically thermal drift. Thermal drift is nothing but the expansion of the transducer and then the load frame and all those things, which can happen systematically with time. So before doing any experiment, you have to first run the sample run the test without sample and to get the thermal drift, and then you have to basically subtract the thermal drift from actually load displacement data to get the actual load displacement information. Second thing is piling up and sinking in. If you see here, this is basically the impression after indenter. And if you see cross section, cut the section, and they see from the right side view, and then you see that there is increasing the material, there is collecting the material surrounding the indenter. Here the material is going down. This is called sinking in, is piling up. This generally observes piling up is observed in mostly anneal materials. This is observed mostly in the cold work materials. Cold work material will not strain harden. Simply it can go penetrate deep into that. So this changes the contact information between the indenter and the sample. Right? Actually, if the sample is flat, and then it from the expression whatever area function is there for a particular depth, that is valid. But if there is a piling up or sinking in there, then actually projected area of the indentation can change. Calculation based on the actually depth from the HC calculated on the load displacement data. This can give extra, for example, here the hardness will be underestimated, here the hardness will be overestimated basically. So these piling up, sinking in, you have to consider before actually make a valid judgment of the data. And the third one basically indentation size of it. Because since the loads are very low, like in micronewtons, you can't keep on decreasing the load to get the surface information. Because what happens at the surface, sometimes there is an oxide film will be there, sometimes surface roughness will be there, and the surface sometimes actually deformation zone itself is not sufficient. Because to get an indentation, you need a plastic zone. When you do the indent, may not be having the plastic zone enough to capture the actual data. So that means what happens at the initial loads, initial depths, by changing the indentation depth, the hardness can change. But beyond certain depth, by further increasing the hardness, depth of the indentation, your hardness will not change. That means after that, there is no indentation size effect. Below that depth, there is a size, indentation size effect is there. So most of your hardness you should measure in the range of where there is no indentation size effect is there, so that you can actually get the actual information. And the fourth one is basically very important, is tip area shape function. This is how the tip initially looks like, but after some amount of usage, the tip become like a little dilated. That means the area function which calculated the constant into HC, right? The constant coming from this kind of area function, right? Because they're doing different indentates on a known material, and then you can curve fit that one, and you can get the C1, C2, C3, C4, C5. From there, you can actually get the area function, right? That is basically from that you can get the constant. Where for example, for Berkovich around 24.6 something, right? And multiply with the HC will give the projected area. But if this area shape or shape of the tip will changes, then the constant will also has to change. That means you have to, in a frequent interval of time, again you have to take a known material and do some number of indents and then curve fit that one, and again you have to generate a new area function, and you have to use that area function to calculate the hardness. If you're not doing area function frequently, you not calibrate the machine, again you're going to get the erroneous hardness values. This is how the area function changes as a function of that. This is initially like this, but it can change. So now this is how I finish the nano indentation. Now I take two case studies where we have done micromechanical testing. Micromechanical testing mostly in situ mechanical testing, or sometimes ex situ also, where the samples are in size in micron scale. So here, first thing what I do is we take a magnesium material and we make a pillars in the focus ion beam milling where you can remove the material. I will discuss, I will show you in a minimal time, in a short time. And then you can do the micro deformation, and also the same samples you do the macro also, and to see how the deformation or behavioral changes from micron to macro scale. And also we do different geometries also we tried when I'm in Oxford, and I'm going to show a couple of slides on that. So for example, this is a magnesium bicrystal basically, and I have to acknowledge to Professor Watanabe to be kind enough to give some bicrystals to us. So this is basically a particular orientation. This is a particular orientation. This is how the grain size. This is basically magnesium is basically HCP crystal structure, right? HCP structure. This is how the magnesium micro units are. This is HCP. HCP has the two prominent slip systems, which are basically participating in the deformation at room temperature. One is basal slip system and is a prismatic slip system. On the top, there are two more slip systems, are the pyramidal and second order pyramidal. This will not participate. Depending on the CV ratio, sometimes some materials, CV ratio of HCP is basically, C is basically this one, A is basically this one. CV ratio basically dictates which slip system, either basal or prismatic, which actually dominates. In magnesium, where the basal CV ratio is 1.633, close to the ideal, the basal slip system is more dominant. The CRSS of the basal slip is much lower than prismatic. That means if the CRS is aligned 45 degrees to the tensile or compression axis, where the resolved shear stress is more, and because applying stress like that, using the Schmidt factor, actually can calculate the resolved shear stress along this plane, where the shear stress is maximum. If your basal planes are aligning like this, that means the shear stress on the basal planes are much more, and also basal planes are actually the slip systems. The slip can happen easily. Instead of that, your basal planes are aligning either along the direction of this one, or basal planes are aligning perpendicular to the tensile direction in the compression direction. Then your Schmidt factor, where either lambda or theta is going to be 90 degrees, and your Schmidt factor is going to be 0, and the resolved shear stress in this along this planes are 0. That means the shear stress on the basal planes is almost 0. That means slip happening is very difficult. In that case, for example, if basal planes are along in such a way that your C-axis is under extension on compression, then twinning can get accurate. This is the twin planes. For example, if you compress like this, right? For example, here the unit cell is orienting like this. Here the unit cell is orienting like this. We apply, this is mostly close to this kind of configuration, right? That means your resolved shear stress on the basal planes is much higher. That means this grain is much more favorable for slip actually. Here my basal planes are 90 degrees to the tensile compression axis. That means here the slip, the happening slip is much more difficult. On the other hand, my basal C-axis is under extension. For example, if you press it like this, my C-axis is going to expand, right? That's why here this is more prominent for tensile feeding. So basically here this orientation is mostly for the slip dominant. This is mostly basically twin favored orientation. So now I make a pillar here and make a pillar here, and I'm going to do experiments actually. Basically, this is how I make the pillar here. Basically, by using the focus ion beam is another SCM kind of tool where they use the gallium ions to remove the material wherever you don't want it. So take a sample of this particular, for example, this sample, put into the SCM, and I remove all the material, left it with some pillar, right? If we compress it, it's kind of similar to the compression experiment, though there is a constraint in the bottom, but it's almost close to the compression, right? So basically, this pillar dimension is around 5 microns. This is around 7 microns. This is around 3 microns, I guess. Is basically the pillar dimensions, and we use the 2 nanometers. These are basically what kind of parameters we use for during the milling. Actually, make sure that there is a less damage to the pillars because of the ion beams, right? That should be make sure you have to make sure that there should not be any damage during the ion milling. And at the same time, we're taking this material and this sample and make a macro compression samples. Like macro compression means basically 3 mm by 3 mm cross section and 4 mm height. This is rectangular compression samples we made out of that. And we did the macroscopic compression experiments at 10⁻³ per second strain rate also. So first you see, this is how the microscope, this is a pillar, and then we apply the load. And then when you apply the load, first basically this is a slip dominated, means you apply the slip. Slip happens along the 45 degrees to the compression axis. See, this is the slip length. So the slip is happening, right? So this is what we are having slip actually. This is what we are recording during the deformation. because by using indentation only, by using flat bench, we can measure the load. From that, you can calculate the strain, the stress, and the strain also. Because from the lower indentation, you get the stress and strain, so you can get the stress strain curve. So this is how the curve looks like. On another beam pillar, you can see the slip lines which are orienting 45 degrees to the tensile axis, right? And if the stresses are almost like constant, there is not much significant strain hardening we are seeing. Once you reach the elastic limit, yield stress, it's almost like there is a basically pop-ins are there, because each slip line active, there is a drop is there, right? Like when activated upon the activate of each slip line, you can see the drop, right? But more or like there is a no strain hardening. Strain hardening is almost absent. That means there is no interaction of the dislocations happening. Slips are going in the planar mode. So when slip line is when dislocation is active on a particular slip line, it is going to the other surface. It is not interacting between the slip line, dislocations. When there is no interaction, you're not seeing much strain hardening. Serrated flow, you're seeing no strain hardening, lack of mobile dislocation interactions. But at the same time, this is basically a twin oriented. Means basically you're expecting twinning. You're not seeing any slip. So when doing deformation like that, then you're not seeing any slip, which is 45 degrees of tensile axis. Rather, it's mostly like you have seeing a basically twinning. You see the twin. See, that's something, then finally going to get fracture, right? So that you're saying basically, this is how the sample looks like after deformation. And then this is how the stress strain, because there is a sudden drop is there. There is no artifact because we did interrupted test. There also you seeing this drop is there. And then there is a significant amount of strain hardening, which suggesting that here we are seeing a yield drop. At the same time, we are seeing a plateau. And then there is a volume change of 5 to 6% is there, and also showing anomalous strain hardening behavior, which is completely different from the typical slip dominated pillar, slip favored pillar. So then these are the basically macroscopic samples. These are oriented in slip orientation. These are twin orientation. So forgive me for the bad surface finish, because these are the damage from the soap water. But finally, we could get the, let's see what is happening in the slip. We are seeing a lot of slip bands, right? Seeing a lot of slip bands here. And these are more interactions are there. There is some amount of twinning is also there. But here only twins are there, which is perpendicular to the tensile, which we observed in the pillar also. They are perpendicular to the tensile axis, compression axis. And I want to further notice that these are single crystals. These are not polycrystals. These are all experiments you have done under single crystal experiments, right? That's why you see anisotropy also sometimes. So this is how we compare the true stress from the micro pillar and from the macroscopic for the slip oriented and twin oriented. And here again, the strain hardening is observed both in twin oriented, microscopic and macroscopic. It is almost absent in the microscopic and macroscopic of slip oriented. So what from this you can judge is that there is I didn't present here, but I could see that there's a lot of dislocation interaction you could see in the slip oriented, in the twin oriented. So these dislocation twin boundary interactions create further dislocations, and this interaction actually started doing significant amount of strain hardening, which is not there, which is mostly like a planar kind of slip, and which is presented in the slip oriented, and you're not seeing much strain hardening. So this is behavior. So the same magnesium, pure magnesium, in particular orientation, you're seeing different behavior. Another orientation showing different behavior. So it itself is suggesting that material anisotropy and material orientation plays a significant role in the deformation behavior. If the polycrystal randomly oriented, you can do in deformation in particular direction, it can fine. But if a single crystal or highly oriented grains are there, then you have to definitely probe the mechanical properties in different directions to see whether there is anisotropy existing or not. And then we also did in Oxford, this is basically commercial titanium pillar. Basically, what is the advantage? What we want to study is that when you apply a load, this is basically you develop a tensile stresses here. These tensile stresses create dislocations, and you put a grain boundary here. All these tensile stresses were going to interact with the grain boundary. That is one of the objective of this thing you have done on this sample. And further, what we want to do is basically we want to calculate back stress. Basically, for example, what is the effect of cyclic loading? The geometry of the cyclic loading is very difficult. Produce a cyclic loading in the micro tensiles and micromechanic testing is very difficult. So we came up with our own geometry. It's called seesaw geometry. For example, apply load like this. Basically, this is how the beam looks like. Apply load like that. For example, you're applying load at this position by using nanometer, then this portion will be compression, this portion will be tension. Then if you change the load to this one, then this portion will be tension, compression, this portion will be tension. So you can apply the load, tension, compression, again, cyclically you can apply. In same sample, one time you're applying tensile stress, and that time you're applying compression stress. It's the same time here, one time you're applying tensile compression stress, and they're applying tensile stress. So you can see what is the effect of cyclic loading on the mechanical behavior. This is how we made the before deformation, how the CSA sample is there. This is after deformation. See, you're seeing the impression of the indenter, right? This is basically the Berkovich indenter. Then we push the sample point load in this direction. This is how the, for example, one load initially loaded in this direction, unloaded it, again loaded in this direction. The strain for further plastic deformation increased, again unloaded it. Now I change the direction from here to here. Then immediately the load in this direction, the deformation for the strain is plastic, the onset of the plastic deformation decreased. And then further again unloaded, again loaded in the other same direction only. Again it's increasing, again unloading, again loading, again increasing. So in the same direction, if you load again and again, the onset of the plastic deformation increasing every subsequent cycle. Whereas if you change the direction, immediately the onset of the plastic deformation is decreasing. That's what we observed from this material. So from this, I want to stop my presentation. Thank you very much. Hello?
Yes, sir.
Thank you very much. So this is, I want to stop now. So in this whole talk, which we initially talked about, there is a importance of different mechanical characterization tools depending on what kind of loading, what kind of loading rate, what kind of loading pattern, what kind of stress state. You have to change the mechanical characterization technique to characterize the mechanical behavior. And then we see what is the uniaxial tensile machine. We compared with we classified the mechanical techniques, different mechanical techniques, and then we also discussed about the uniaxial mechanical testing machine, how to do compliance correction, and then we talked about different extensometry techniques, and then DAC, and then we also talked about the micro scale testing, is nano indenter, and then nano indentation. Then finally we have some case studies on the micromechanical testing. So with this I conclude my talk. Thank you very much. Thank you.
Thank you very much, sir, for this very informative session. Now,
Thank you
participants can ask their questions by using raise hand option. And if participants raise their, sir?
I can see the raise hand here.
Sir, I'll unmute the person who will raise the hand, sir.
Okay.
So that they can directly post.
Okay, you are going to basically moderate that. Thank you.
Yes, sir. Yes, sir. Someone, Dr. Sampath G. Deshmukh, sir. I am unmuting you, sir. Please ask the question. Dr. Sampath, sir, unmute yourself.
Hello.
Please tell me.
Hello.
No, please tell me. Please tell me.
Is audible, sir?
Yeah, I can hear you.
Sir. You are nice, sir.
Thank
informative.
you. Thank you.
I want to ask a question. At the scanning electron microscopy, you have seen the image.
There is a breaking in your voice. Your voice is breaking. Please. Hello.
Deshmukh, sir, your voice is not audible, sir. It is getting broken. Hello, sir. Hello. Deshmukh, sir. I think he got offline, sir.
Yeah, please.
We'll
I think
take
something is asking, but I couldn't hear his one. The complete question I couldn't hear.
Yes,
We can
sir,
type
yes,
possible. They can type the question, then we can tell, right? That is much better, I guess.
Sir, there is a question from chat box, sir, from Dr. C.V. Subramaniam, sir.
Okay.
He's asking how to test polymers and ceramics.
So yeah, that's what in polymers, what you're going to look is very important. Ceramics, what you're going to look is important. Ceramics also we can test what finally you want it. Ceramics, tensile test ceramic is very difficult because if you make the tensile cells, there is small misalignment, it's going to break the sample before going reaches maximum load because these are very brittle. So mostly ceramics, we use compression samples, and the strains even compression at room temperature is very less. So you can, so what is the maximum fracture strain you can get from that in the uniaxial tensile machine. But when you're doing compression, since the stresses are quite high, you have to use a platens between the sample and the top, between the sample and the platen, so that it will not indent the platens, right? So that okay. And then in the polymers, mostly you see a non-linear elastic behavior. So when you go into polymer, you have to tell what strain actually you are basically measuring particular stress. For example, if you take metals, you will see basically yield stress, mostly it will 0.2% yield stress, and then UTS. You can tell like that. When the polymers, you can't tell like that. You can tell, okay, it's 0.5% strain, what is the stress? What 10% strain, what is the stress? Because this chain is elongating, the non-linear will be there. And again, we have to do more experiments. You have to do so that there will be more scatter will be there in the polymers. So to do more tests, you have to do. And another important thing we have to do in the polymer is that you have to do loading unloading curve and see how much hysteresis loop is there. If it is a less viscoelastic behavior, then the loading and the hysteresis loop will be much lesser. So that is very important study. And also you can study the loss modulus in the polymers by using a cyclic stress strain curve. Further, you have to use dynamic mechanical analyzer, not necessarily nano-indentation, but there is a dynamic mechanical analyzer macro tensile macro machines are there where you can use a bigger samples. So you can apply a sinusoidal loading pattern. You can apply with different frequencies, and from there we can get the phase change. From there we can capture this loss modulus. That is very important for the polymers or soft matter based any biomaterials.
Sir, from chat box, Sandeep Deshmukh, sir. Will you please help us to do scratch test for micro level coatings to correlate with micro hardness for SG iron WC samples coated with tungsten?
You want my help? Is it machine or what?
He's just chatting, sir.
No, that's what I don't know. He wants to know how to do. I think the technique will be there where you have to apply load and then you put some particular normal load. You will drag with particular velocity, and from there you can get expressions. We can get the scratch hardness and other things, and also how the depth as a function of scratch distance is changing everything. That's we can do.
Okay. Another question from Rahul, sir.
Yeah,
Tensile test of aluminum alloy composite material, cross section of specimen should be rectangle or circle. How to select, sir?
That is again what you're going to do. For example, if you want to measure the particular area of microstructure continuously, for example, if it is a circular section, for example, applying the micro, if it's not a isotropic material, it's not a isotropic material, it's an isotropic material. If you see the microstructure in particular place, and you diametrically 90 degrees, you see the microstructure, they may look different, right? You can't do comparison study. First thing, for example, if it's a flat sample, a rectangular cross section, all the time you can see the surface of the sample for all the materials at different loading directions, at different heat treatments. But at least you can see how the microstructure is changing as a function of different process parameters, a different load in testing parameters. You can see that time rectangular cross section sample is much more important. For example, you want to do EBSD, you want to do hardness of the tensile samples, then rectangular cross section sample is important. Hello.
Sir,
Yeah.
okay, sir.
So depending on what exactly you're looking for, more material is there, and cylindrical is, and is basically kind of extrusion material is there, extruded material, which is axially symmetric. Then you can go with cylindrical sample also. If it's a roll material, then the cylindrical samples may not be suggestible. The sheet sample is suggestible because it's orthographic symmetry. Because the rolling material, the symmetry, along rolling direction, normal direction, transfer direction, three orientations are there. This is orthographic symmetry, right? Their sheet samples are much better. It's an extrusion sample, which is a cylindrical extrusion sample. Those are axially symmetric, the microstructure, texture, everything. That time roll sample, cylindrical sample is also fine. Our sheets are okay.
Sir, another question from Patri Sridhar, sir. For friction surface samples, how scratch test can be conducted? For example, aluminum alloy 3003 over mild steel.
Yeah.
So that's all.
Yeah, you can take the weld zone and you can do the scratch test there.
Sir, Sandeep Deshmukh, sir.
But one thing is very important is when you go into micro scale, scratch test is fine. Macro scale scratch is fine. When you go into micro scale, nano scale scratch test, we should be always careful about the microstructural length scale in the particular area where you want to measure. For example, some people actually put the precipitates and then do friction stir welding. The precipitates will distribute over a micro in the general precipitate spacing maybe 100 microns, 50 microns like that. And the precipitate particle size itself is 20, 30 microns, 40 microns. Then doing nano indentation, there is no use. Their land scale, then better to go to the macro based scratch test or macro based indentation test is important. Then you get a much more uniform information you can get. Otherwise, if you use nanoscale, then you get a lot of scatter in the data you will get. So what is your microstructural length scale is also very important while choosing what kind of test, what scale of test you are using. Going to do.
So thank you, sir. From Pranav or sir, how can we test for titanium aluminides since they are brittle in nature?
Exactly, yeah. That is a common problem for any brittle material. We developed in high entropy alloy, which is very good strength, but the brittleness is so high. If you do tensile experiments, they will break, right? So mostly the people uses compression experiments, but the ductility you're going to report from the compression experiments, people won't believe it. If you want to really people believe your ductility, you have to go for tensile tests only. There is no other alternative. But you have to make sure that your alignment of the top grip with respect to bottom grip is perfectly aligned, the top and bottom grip, and your sample should be properly aligned with the sample axis. Sample loading axis is properly aligned with the axis of the loading train, as I mentioned earlier. If you have any misalignments, the sample is going to break very fast because the stress concentration developed at the shoulders will be enormous, and then you can immediately get sample get fractured. So if you really want to get the ductility, you have to use tensile testing only. Or you just want to measure the strength and other things, compression experiments are fine. If you do tensile ductility, then alignments have to be very careful with alignments.
Sir, there was a question from Mr. Bharat Susen Admiral earlier, sir. What are characteristics differences between measuring micro hardness from regular hardness measure, say BHN?
No, BHN you can do even in a micro also. For example, there are two types of micro hardness things are there. Micro is there without instrumented hardness. With instrumented, micro and nano is there. Where instrument is there, you get a low displacement data. Without instrument, we can you can choose the area where you want to indent, and you can either use a loop indenter or you can use the Vickers indenter. Generally, people use these indenters, and you can get the indentation. And if you want to compare you get the same indentation Vickers, you can do macro also, right? But they may not necessarily be the same, because the deformation zone under the macro indenter much higher than the deformation zone under micro indenter. For example, microstructural length scale is very important. If a microstructural length scale is very coarse, then macro to micro will have a difference will be there. Microstructural length scale is very fine. Your grains is very fine. Our precipitates are very finely distributed. Then microstructural length, then micro hardness and macro hardness, you can give both same, because the deformation zone in micro hardness can consist both precipitates and the matrix, and the deformation zone of the macro hardness also consists both deformation precipitates and matrix. That means you can get the total combined effect. Then it can case both should give the almost similar results. But if the microstructural length scale is so large, then macro scale will give different results than micro scale. Okay. Sir, I hope I answered his question.
Yeah. Sir, Shashidhar ji raised his hand. He want to ask you a question, sir. Shashidhar sir, you can unmute yourself and ask questions, sir.
Sir, good morning, sir.
Good morning, please.
Sir, assistant professor in GMR Institute of Technology, Raja.
Please tell me.
Sir, while doing lab practice in hardness testing, you are facing to find out the depth of indentation.
Can you please repeat?
Hardness testing, sir.
Huh?
Yes, sir.
Large testing, I didn't understand.
Hardness testing, sir.
Hardness testing, okay.
Yeah, BHN only. Ball indenter, sir. But how to measure that H, sir, depth of indent manually?
For ball indent, why you want depth of the indent? Just you have to measure the diagonal of the indent.
No, actually, we want to cross check that ASTM formula, sir. We have ASTM number.
So you want to measure the depth of the indentation, right?
Yes, sir. H.
There are two things are there. Basically, there are surface interferometry techniques are there. Optical interferometry and AFM, these kind of things are there. AFM may not be suitable because the depth of indentation is too high. There is a optical interferometry things are there, where the fringes will be there. You put the fringes, optical fringes, you will put on the sample. When there is a depth difference is there, you will see the difference is offset in the fringes. From the offset from the fringes, you can actually calculate the depth of the indentation. Right?
Okay, sir. We have to purchase that device.
No, I think but you don't need to purchase. There are places where you can get in. I think in IIT also we have that optical instrument there.
Okay, sir. Thank you.
Yeah, please.
Sir, Dr. Sampath G. Deshmukh, sir, raised his hand. Sir, Deshmukh, sir, hello. Unmute yourself. Yes, sir. You are audible, sir. Hello.
Yeah, please.
Hello.
Please tell me.
Audible?
Breaking your voice. Your voice is breaking.
Sir, is audible?
No, it's not. It's breaking. Please.
Sambat sir, it's better if you write. Yeah, it's breaking, sir.
It's audible now.
Sambat sir, it's breaking, sir. It's better if you write a message in the chat box. So we'll go for another participant, sir. Dr. Swagatika Mishra.
Please.
Madam, please unmute yourself and ask question, ma'am. Swagatika Mishra, ma'am. Yeah.
Hello, sir.
Yeah, please.
Hello.
Please tell
Madam,
me.
a bit louder, madam.
Hello.
Please tell me.
Sir, what's the difference between the macro and micro harness? If the micro harness testing machine is not available, can we use the macro harness testing machine for the purpose of testing in like Inconel material?
So exactly what you want to measure in Inconel? What is the condition of the material sample?
Sample is Inconel.
No. Is it heat treatable? Is it rolled or it's a?
No. The material is EDM machine material.
EDM machine, is it?
Yeah.
No. What is the condition of the material? Basically, what heat treatment you have given, or what?
No. Condition of material.
It's a as cast. It's a as cast, is it?
The material is not heat treated. Only we have done the material that EDM machine.
Yeah, that's fine. But what is the history of the material? Basically, it's a as cast material or it's a wrought material. Wrought material means after casting, they do some forging and all those things. For example, whatever it may be, you just measuring the hardness as a function of what you want to measure. Generally, Inconel people do hardness as a function of aging time. They do aging at different temperatures and then do measure the hardness as a function of aging time. In that case, you can do the macro indenter also. Brinell, anything you can use it. Not a problem.
Okay.
Sir, another resident from TCH Anil Kumar, sir.
Yeah, please.
Anil, sir, please unmute yourself.
Sir, good afternoon, sir. Is my voice audible?
Yeah, I can hear you.
Sir, very nice session, sir, from you. Actually, I missed half an hour session due to meeting. The thing is, sir, actually, I am facing two types of problems, sir.
Yeah.
Whenever we are dealing with aluminum alloys to observe the microstructure, it's important that etchant, we know the etchant, but how much time we have to wait that we are unable to.
So you're using cross reagent, is it?
Yes, sir.
So that actually you have to trial and you have to optimize the conditions to yourself. We are using around 10 seconds. I think our student is using. So basically, actually aluminium alloys you can do nicely electropolishing also. If you have electropolishing. Yeah, very good surface you can get. Once you get the surface, then you can do etching also. So electropolishing can do very nicely. So you can use electro etching also. You can use it. If not possible, cross is sufficient because it's very standard polish etching aluminum. What is the alloy composition?
Yeah. We are using Inconel, sir.
No, you told
I didn't remember the combination.
No. You told aluminum, right? You told aluminum.
Sir. Sir, aluminum. Actually, we are using 8000 series, sir.
8000 aluminum lithium alloy, is it?
Yes, sir.
I think there is cross is there, and you have to optimize it, and that's it. You can't help it.
Okay. Generally, if you tell the time window minimum this time to this time, any suggestion?
No, I can tell 15 seconds. We used to do 10 to 15 seconds, but then it may not work to you because our composition is completely different from yours, right? We are using basically pure aluminum. Sometimes I used recently we are using aluminum zinc. We are using 700 series and aluminum copper 200 series, 2000 series, 7000 series, 7000 series. There is lithium, and that is different the chemistry from your material, right? So you have to optimize little bit. That's all. You have to optimize it. Yeah.
Okay.
Yeah.
The another thing, sir, while we are doing the micro hardness test, we actually do the consultancy type of work at our university also. So most of the time we used to get the dental samples, which is like our teeth.
Yeah. Okay. Ceramic samples.
Yes, sir.
Ceramic samples.
ceramic samples.
Yeah.
So we face a lot of struggling seeing that diamond micro aperture, that diamond shape aperture will be there, no, sir?
Yeah.
That is very hard to read. Any suggestion?
You mean the Vickers impression? Vickers impression.
Vickers micro hardness test. Yes.
Vickers impression. You mean?
Yeah.
Yeah. Because the indentation size itself is very small, I think, right?
Yes, sir. Very small.
And you can do one thing actually.
Sir.
Yes, I don't know. I never had this kind of problem. But if you make the indentations, if you make the indentations and put some kind of dye in that,
Yes.
Some dye you put it, then the reflection will be different. Then I think you can better. You can see the edges of the things. You can much better. You can manage. I think you can get it. I think so. This is my opinion. But I never had this kind of issue with me.
Okay,
but you can do in the SEM, right? SEM you can measure nicely.
SEM, okay.
SEM you can measure nicely, or in the optical with polarizing light you can measure nicely, or optical dark field you can measure nicely. Because if you you may not measure in the machine, micro tensile machine, micro hardness, but take the sample, put it in the optical microscope, use the either dark field, or by changing proper the filters will be there. But then you can easily see that. Then you can measure there and you can calculate it. If you not put it directly SEM, of course you can easily measure there. That's not a problem. But instead of going to SEM, better to go through optical is better. ONS will go to SEM.
Okay, sir. Thank you for your suggestion, sir.
Okay, welcome. Thank you very much.
Sir, another raise hand from Suman Kumar Saurabh, sir. Suman sir, you can ask question by unmuting yourself. Suman sir, hello.
I think it's better we go for the second question.
Okay.
By Mr. P. Sridhar.
Okay, sir. Sir, it's next question is by Patri Sridhar, sir.
Please.
Sir, good afternoon, sir. Sir, it's a very useful information for me, sir. What you have delivered, sir.
Thank you.
Thank you, sir. Thank you, sir. Sir, one thing, sir, I want to ask one question, sir. Sir, here friction surface sample is there, sir. We have friction surface.
Friction steel sample.
Friction surfacing, sir.
Friction surfacing. Okay.
Yes, sir. What that means we are going to quote another meter over the other, sir. Friction steel will nothing meant where the 2 meters we are going to
exactly. Drastically mix it up. Yeah.
Yes, sir. So in friction surface, how we can do the tensile test, sir? For example, if we go for butt joint or some friction steel buildings, we can see the butt joint. Clearly, we can cut the that particular specimen as per dimensions. We can have, or as per ASME or ASTM, we can carry out. But if we take the friction surface samples, how we can do the tensile test, sir?
So what is the friction surface means? Only the surface?
Yes, I will tell you, sir. Sorry, sir. Sorry for interruption, sir.
No problem.
For example, if you take some mild steel, sir. For mild steel, suppose if we take some other another metal, maybe some if we take let us I'm taking aluminum, 303, which is a combination of aluminum and magnesium, sir. So manganese. So over that, aluminum. I'm giving some do that rotation. I'm going to deposit that particular aluminum 303 on the mild steel, sir. Coating, just like coating.
You're depositing using electrode deposit, something like that?
It's the same like that. Like that hard facing or thermal spring like that, sir.
No, you're depositing using some coating technique, is it?
Yes, coating technique, sir.
What technique you're using? Coating technique?
So it is suppose if you fix that is in the form of aluminum rod form, sir.
Okay, fine. What is the length scale of this layer? What is the length scale of?
It's 2 to 3 mm, sir. 2 to 3 mm.
The layer itself 2 to 3 mm, is it?
Yes, sir. Hardly up to 5 mm, that's sir.
So thickness of the layer is 2 to 3 mm. So you want to measure the mechanical properties of the thin film or the mechanical properties of the interface?
Interface, that particular base metal, and also that coating, sir.
Coating for 4 mm is so big, so thick actually to make tensile samples. We are making tensile samples thickness of 0.5 mm.
0.5 mm.
These are not ASTM standards. You have to scale down to the lower subsize. But you can do. Basically, you use the EDM cutting. You have to use it. You have to use the EDM cutting. to cut the
Okay,
sample,
sir.
and then you have to use EDM. You can easily make a, if 3 mm is there, you can make easily samples of 1 mm easily, can make using EDM. Once you
Is
make
the
the
coating
EDM slicing, once you make the slicing,
okay.
then you can cut
Okay,
and
sir.
measure the string. Yeah. But the
No,
interface
sir.
measurement is difficult. Interface is difficult.
Yes, sir. But one thing, so if you see the dog bone structures, we can see some radius of curvature, the particular gauge length, everything we can cut, sir. But how it happens here, that's a doubt, sir. In this one, in the particular this one.
For example, can you see me?
Yes, I can see you. I can use, yes, sir. I can see you,
For
sir.
example, this is your material substrate, and this is, for
Yes, sir.
example, 1 second.
Sir.
This is your coating, right? This is your material. This is your coating, right? This is how you done, right?
Yes, yes, sir. Okay, sir.
So now what you do is you have
yes,
cut
sir.
the tensile sample like this, and then take the sample like this and slice it like this. Then you can get the tensile sample.
Okay, sir.
And at the same time, you can get the sample from the substrate. But the interface getting is very difficult.
Okay.
But actually, you can go to very small samples, very small sample sizes. Then you can do interface also properly by polishing. But the sample is too long, then polishing is difficult. For example, 10 mm sample or 20 mm sample size is there. Then you can properly polish to the both sides so that your interface is at the center exactly. That you can do. People are doing even micro samples. People are doing it. The 3 mm is so big, you can do easily. That's not a problem.
Big. Okay.
But you have to develop a grips. You have to develop a grips to hold the samples.
That what, sir? That what?
You have to develop a grips to hold the samples. We can discuss not now. We can discuss later. Not a problem. We had our own grips. I can show you how to give the grips. For that, I should know what machine you're using. So we can contact mail. You can mail me. We can discuss. Not a problem.
Okay,
but you can,
sir.
In principle, you can. We are doing 0.5 mm thick samples. You're doing.
Okay, sir. So one more question, sir. Sorry, sir.
Please.
Sir, same thing, sir. The substrate is MySteel, sir. Over MySteel, aluminum 303. So aluminum is etching in this careless agent, sir.
Aluminum 303 means basically aluminum magnesium. Aluminum manganese, right? Yeah.
Sir. Sir. Careless agent, sir. Careless agent etchant we are going to use the relieve the microstructure for aluminum 303. For MySteel is nitrile or pickerel, sir. We are going to use.
I'm sorry. Okay.
So etching agents for relieving the microstructure for aluminum is careless agent, sir. Careless agent.
Yeah.
For MySteel we go for nitrile, sir.
Yeah.
But the interface, that means the combination of the aluminum and the MySteel, the interface, how we can able to see the microstructure, sir? Is it possible?
Yeah, you can see. Not a problem. You etch it once and that time, and then etch it this thing. You can see.
But both are different, no, sir. Aluminum is different.
Once etch with that one, once another etch with this one.
Can we get the interface structure, microstructure?
Interface, I don't. Then you have to go to SCM actually. I think so.
SCM. Okay.
Yeah, SCM you have to go. Where in the BSc you can do properly. Be a backscatter electron detector. You can get the composition contrast. Then you can properly see how the microstructure changes from the one from the substrate to toward the film, and also how the adherence along the film, any porosity formed at the film interface. All those things you can see SCM.
So by SCM we can see the structure of the interface.
In BSc, without etching you can see BSc.
Okay. Thank you, sir.
Then etching is also not required actually. You can, in the backscatter detector, you can see the composition contrast. There you can see all those things. Okay.
So thank you, sir. One more raise hand from Sandhya Rani, madam. Madam, unmute yourself and ask question.
Sir, good afternoon, sir. Sir, my research work includes that hybrid composite material, sir. Hybrid composite materials. One is natural fiber, another one is carbon fiber, sir.
Okay. Matrix any?
Matrix, epoxy and hardener.
Okay.
So in that work, alternate layers are there, sir. One is a natural fiber, means a snake plant fiber, sir. Another one is carbon fiber. One layer snake plant, another layer is carbon fiber. Like that, up to 3 mm thickness. As per ASTM standards, my work completed, sir.
Okay.
But my question is it possible to change the directions also?
The direction of what?
In my work, only uniform direction. only one direction.
Okay,
In that,
basically, yeah. It's a fiber
yes, sir.
reinforced it's a fiber reinforced composite actually. Yeah.
Yes, sir. Yes, sir. Tensile completed, mechanical properties, all tensile compression and SEM also completed, sir. But in that work, only one direction is there.
There will be anisotropy will be there in the mechanical properties, right?
Yes, sir.
And they do the tensile test at different directions and see how things are there. And also what is the fracture behavior, because fracture mode is maybe different from tensile to if you change the orientation of the tensile axis along the fiber and 45 degrees to the fiber and 90 degrees to the fiber direction, the fracture behavior will be different. And fracture studies you can see, failure things you can study.
Yes, sir. Only one direction we have to take in.
Yeah, you can should see the anisotropy in different directions, how things are there.
Okay. We can that one also.
Yeah, you can cut the samples along the different directions because it's a sheet, right? You can cut the sample like this, you can cut the sample like this, you can cut the sample like this.
Yes,
you can change the orientation and see how the mechanical properties and how the failure modes changing, because failure modes you should study in these kind of materials. Failure mode.
Yes, sir.
Is it fiber pulling or fiber fracture? All those things.
Yes, sir. Yes, sir. Thank you, sir. Thank you.
Thank you very much.
So, our next participant is K. Praveen Kumar Reddy.
Yes.
Sir, Pavan Kumar Reddy. Sir, Pavan Kumar Reddy, sir. Please ask.
Yes, sir. Yes, sir. Sir, good afternoon, sir.
Please, sir.
So, this is Pavan Kumar Reddy from JNTU College of Engineering, Pulivendula.
Okay.
Sir, actually, my question is, I am working on aluminum alloys.
Yeah. Which alloy?
Sir, actually, aluminum alloys. Sir, I have measured that residual compressive stresses through the portable residual stress analyzer, sir.
Using XRD, is it?
XRD. Yeah. XRD as well as portable residual stress analyzer. That's different.
Okay.
Sir, here in two instruments, I got FWHM, sir. That is a full width half maximum.
What is the medium in the portable one? That is also X-rays only?
X-ray only, sir.
That is also X-ray. Okay.
It is also X-ray only, sir. But equipments are different.
Both are different.
Here I have measured that compressive stresses, and here I have measured in XRD analysis that I measured FWHM, sir. Sir, is there any difference between that FWHM in both instruments?
Yeah, it will be there. It will be there, right? Because the FWH includes the machine broadening and broadening because of the residual stresses, and also sometimes there's a peak shift will be there depending on the lattice parameter change, and all those things will be there. But machine broadening is very important. Machine broadening is very important. We have to neglect that thing using a standard, very coarse grain and a fully annealed material. You have to put there and see what is the broadening so that you can deconvolute the machine broadening from the sample broadening. Then you compare it.
Okay.
And and one more thing, the source is same in both techniques. X-ray source.
X-ray source is not. It is different for both the instruments, sir.
What is that? No. X-ray source, not the source physical. I mean, cobalt source or copper source. What source you are using?
Copper source. Both are common, sir.
Both are copper only, is it?
Copper, sir.
Both are copper source only.
Both are copper, sir.
Copper only, right? Then you should then you have to deconvolute the machine broadening. Their machine broadening will be different. Here machine broadening will be different. So you have to remove that one and then compare the data.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Sir, I hope this is the last.
Yeah.
From Rahul Sandanshu. Rahul sir, please unmute yourself, sir. Rahul Sandanshu.
Hello.
Please.
Good afternoon, sir.
Good afternoon.
Sir, I want to ask a very simple question. For a tensile testing of a aluminum composite material, for the specimen preparation, we use either a rectangular section or a circular section, a sheet material or a circular sharp material. So, which one is gives the best result, sir? And why? How to select circular section or rectangular?
What kind of composite you're using?
Aluminum alloy composite.
No, it's a particle-based composite. It's a fiber-reinforced composite.
Fiber reinforced composite.
So, what is the fiber shape? It's a basically sheet-type fiber, or it's a thread kind of fiber,
right? It is a circular rod.
Then both will fine. Both are fine.
Both are fine.
As long as there is no texture involved in the material, both are fine.
Okay.
Because
Thank you, sir.
sometimes some texture can be involved during the processing. Like for example, doing extrusion, right? Then extrusion texture will be there. If not extrusion, what kind of technique you're using to make the composite also very important.
Okay, so it does not affect on any results.
No, if it is a properly randomly oriented, it should not be any effect between these two.
Okay. Thank you, sir. Thank you so much.
Thank you.
Thank you, sir. Sir, one more hand raise, sir.
Please.
And,
There's 11 charts also there, I think.
Yeah. Rohini Kumar, sir, please unmute yourself. Yeah.
Good afternoon, sir.
Sir, your audio is very low.
Hello. Am I audible?
Hello? Yeah.
Sir, good afternoon, sir. I have a doubt regarding tensile test or compressive test which we are conducting on UTM. So those values are correct, or is there any wrong?
Can you repeat? Can you repeat once again, please?
We are conducting a tensile test and compressive test on UTM, universal testing machine, which are in private colleges.
Okay.
Not instrument machines.
Any UTM is fine.
Those data are correct or wrong?
So you are
in your presentation, maybe in third slide or fourth slide, you mentioned that there are different strain rates.
No. Okay. There are
different strain rates.
Yeah.
So in servo hydraulic machines, the strain rates are very.
No, you can do low strain rates also in servo hydraulic, not a problem.
Yeah. In a private college, we purchased universal testing machines in FIA made something like that.
Is it servo hydraulic? It's a servo hydraulic or screw driven?
It's not screw driven, I think so. It's a servo hydraulic.
How much it is? If it's too expensive, then it's a servo hydraulic. If not, then it's screw driven.
So it's 1.5 lakh maybe.
Then it's screw driven only. Yes.
Yeah. So then, what about that conditions, sir? Whatever the data we are getting, is it correct or wrong?
It will be correct only. What is it? No, basically any machine. Okay.
Yeah.
One is cross-head displacement is there, right?
Yeah.
From the cross-head displacement dictates what strain rate, because strain rate is nothing but cross-head velocity by your gauge length, right? Okay. First gauge length. Basically, you do the strain rate.
Yes.
So basically, you're doing for the same cross-head gauge length, increasing the velocity of the cross-head, you can increase the strain rate. But you can't continuously increase the strain rate because there is a mechanical limitation is there. First thing.
Yeah.
Second thing is, first you want to thing is two outputs are there. One is the cross-head displacement, and the second one is basically your what is called your load cell displacement. So those things, if they calibrate, fine. Otherwise, you can calibrate by yourself, right? For cross-head displacement, for example, the same strain rate is going or not. Simply run the test with cross-head velocity without any sample, and plot strain as a displacement as a function of time. It should give a straight line. The straight line or the slope of the straight line is same as what velocity you have given input you have given to the machine. Both are matching, means your cross-head velocity is accurate. Okay. Displacement, for example, you take a sample and do the experiment, and you put the gauge marks in the sample before doing the experiment. Like put some two lines. For example, this is the sample. Put one line here, another line here in the gauge portion, and measure the distance between these two lines using a vernier calipers or something like that. And on mild steel material, which is very well-known material, whose properties are very good, very well-known, and do the experiment and see the distance between the gauge lengths after the test. Okay, and calculate the strain based on that, and see whether the strain is matching with the your strain measuring from the data. From the data. Do you have strain gauge? Do you have strain gauge?
No, sir. No, sir. No, sir.
Then there will be some. Then you have to check for the compliance of the machine.
Yes. Sir.
You have to check if the compliance issue is there, then you have to do the manual compliance correction, which I told you, right? But in the compression, without any sample, just compress it and get the load displacement data. Okay, with a tensile sample, use a very thick sample, very high strength sample, very high modulus sample, and do it tensile test, which will not deform. For example, without a dog bone, just sheet thick sample, deform it, and get the load displacement data, and use that data to correct the compliance of your actual samples. We are the procedure I mentioned, discuss, right? The procedure you can actually correct it. Then you can use it. Not necessarily everybody is having all the equipments, right? So when there is a less number of facilities, where more thought process will put and more sharpen our things, right? See, that's why it's always good to do all these kind of things to get good data. Again, always compare strains. Then when strains are comparable, that means your data is correct.
Thank you.
So thank you, sir.
Thank you very much. I think somebody privately written. I can write to them, right? Not a problem.
Yeah. I hope everyone has got their doubts clarified and
I think.
benefited. Sir.
Thank you very much. Thank you for giving me this opportunity. Thank you very much.
Sir, thank you, sir, for taking your valuable time to share your expertise.
Thank you.
And any questions regarding collaboration? Sir, okay, sir.
I'm sorry.
Sir, our Srikaran sir would like to end the session, sir.
Yeah, please. Here some comments are there. I can write myself right after ending the session also. I think I can send that. Yeah, please. Okay.
Yes, sir. Yes, sir.
Yes, sir. Rajesh, sir.
Yeah, please. Yeah.
Am I audible, sir?
Yeah, please. Yeah, I can see. Yeah.
I firstly thank you for the beautiful session here, sir.
Srikaran sir, your audio is very low, sir.
Very low?
Yes, sir.
I can hear you. I can hear you.
Now am I audible? Sir?
Yeah, I can hear. Yes, please.
Yeah, sir. On behalf of all the members on the board, I really thank you a lot, sir.
Thank you.
On the board.
Thank you.
It was a beautiful session, sir.
Thank you.
On behalf of the organizers and our college team and management also, sir. And we have been receiving private comments, a few comments which they were appreciative of your talks.
I'm sorry?
All the people were appreciative of your talks, sir.
Okay. Thank you very much.
Really enjoyed that, sir.
Yeah.
Thanks a lot, sir.
Thank you very much. Thanks. Thank you.
Everybody on the board, sir.
Thank you very much. Thanks.
Thanks a lot, sir.
Thank you.
Fine, sir. Pradeep,
Thanks, sir.
will you end the session?
Yes, sir. So thank you, sir.
So once again, just I want to tell one that some people write a private comments. They can write a mail to me so that I can reply. My mail ID is rajeshk@msme.iith.ac.in. Okay, because here I can't reply. They can write a mail so that I can reply to them. Okay, now.
Yes, sir. I'll give them your mail ID, sir.
Yeah, please. Not Rajesh
so,
K.
It is just
Rajesh. Okay.
It is just an announcement to the participants. Any questions regarding collaborative working or research work to the sir can be written to him directly to his mail. I'll give his mail ID to you personally.
Okay.
And so thank you, sir. Thank you.
One more thing in that mail, please put the subject saying that related to this meeting. That's all, so that I can connect it easily. In the subject of the mail, you can say today's meeting, the name of the meeting, so that I can connect the thing to the mail. Okay.
Yes, sir. Our participants will follow that, sir.
Okay, thank you.
Thank you very much, sir. Thank you for taking your valuable time to share your expertise with us.
No, thanks.
Thank you, sir. I would also like to thank our participants for participating here. And that's it, sir. Let's meet again here by 10 a.m. tomorrow at same platform. Thank you very much. Happy learning. Have a great day, sir. Have a great day, all.
Thank you. Can I log out now? Thank you very much. Thanks.
Yes, sir. You can log out.
Thank you.
Pradeep, am I audible?
Now you are audible, sir.
Okay. No, increase the sound. Daniel was saying that I'm not literally not audible.
Yeah, but actually, sir can hear you. That's why I left it. Actually, even I can't hear you.
Okay. Are all the participants going? Can we meet for a while after everybody logs out?
Yeah. Okay, sir.